Good morning, good afternoon to all of you as the situation is. Welcome to first AFOMP school webinar. Due to COVID pandemic, last year in June 2020, we started AFOMP webinars and we got a very good response from all of you. And there are a lot of requests to start AFOMP school webinar on some basic topics. But any kind of organization needs time and efforts. So we took your suggestions and started working on it. And now we are in front of you with AFOMP school webinars. So first and foremost thing we did was devising a logo for the AFOMP school. And thanks to Shivam Sharma, our colleague who designed this, the logo. There are 3-4 logos which then were sent to AFOMP XCOM, and this was finally been accepted, and this is the logo. And now the first webinar will be on reference and relative dosimetry of photon beams. Thanks to Dr. S.D. Sharma, who took pain to devise this first AFOMP school webinar. And as you can see it here, that this is on reference and relative dosimetry of photon beams. And there will be 3 talks by the eminent speaker. One is by Professor Sunil Dutt Sharma, whom I will introduce soon, and he will be talking on reference dosimetry of conventional photon beams. The second speaker, another eminent speaker, Professor Rajesh Kincar from TMH Mumbai. He will be speaking on reference dosimetry of small static photon beams. And the third talk will be from Dr. Sudesh Deshpande, Mumbai, all very experienced teachers, relative dosimetry of conventional and small static field photons. So what we are planning is, after first talk, you can go on putting your any doubts or question into the chat box. I will try to collect those questions and put to the first speaker, Professor Sunil Dutt Sharma. After that is over, I will hand over the floor to Dr. Sunil Dutt Sharma to introduce the second speaker and continue the webinars further. At the end, again, overall question discussion we have, and we have a concluding remarks on these topics. And as I talked about, there are very eminent speakers here in front of you for this webinar. I think you are able to see it. Are you able to see it? Hello?
Not at all.
Not at all. Okay. Just once again, I will try to share it. Okay. Okay, anyway, just now I'm going to introduce the first speaker, that is Dr. S.D., who will be speaking on the dosimetry. And meanwhile, I would like to request all of you to kindly keep your audios muted and also videos so that we get a good bandwidth. So Dr. S.D. Sharma will be speaking on reference dosimetry of conventional photon beams. So Dr. Sunil Dutt Sharma is the head of medical physics section, radiological physics and advisory division, RPAD, at a very renowned Baba Atomic Research Center, BARC, Mumbai. After doing his BSc, MSc, he did PG diploma in radiological physics and then the PhD. His research areas are development of radiotherapy equipment, dosimetry instruments, phantoms and dosimetry methods, radiation dosimetry, QA dosimetry in radiotherapy, diagnostic radiology and radiation safety. He is a teacher for the PG diploma radiological physics and many other courses. He is currently the president of the MP Association of Medical Physicians of India in a second term. He has published for 120 papers, abstract about 180 and 25 others, very long experience. He is associate editor of the JMP and reviewer for many other things. And as you can see, he has contributed hugely for development of the medical physics and also research. He is a member of the AERB. Without taking more time on this thing, he's a very well-known figure in India and abroad for his medical physics activities. With this short introduction, I invite Professor Dr. S.D. Sharma to start his talk. And again, I request all of you, whatever questions you will have, try to put into the chat box. I will try to collect all those things, and then we can have a lively discussions, and your queries, questions will be answered by Professor S.D. Sharma. So now, floor is yours, Dr. Professor S.D. Sharma.
Thank you, sir. First of all, I like to take the opportunity to thank Professor Arun Chowgale and team of AFOMP for organizing the school and giving us the opportunity of having the inaugural AFOMP school on medical physics. So, as Professor Chowgale said, I will be talking on reference dosimetry of conventional photon beams, and I hope this topic is very important and of interest of many of you. I hope you are able to see my slides.
Yes, we are able to see it. Fine.
Okay, thank you very much. Thank you. In radiotherapy, we wanted to deliver the prescribed dose to tumor in various techniques, because now we have available variety of equipment. Some methods are conventional methods. For example, historically we used to treat patients by parallel opposed beam, that is two fields technique, three fields technique. Later on, we switched over to 3D conformal radiotherapy, and the further advancement of the 3D conformal radiotherapy, intensity modulated radiotherapy, and osteotactic radiosurgery and radiotherapy. So the category 1 is usually called conventional photon field, and the category 2, that is intensity modulated radiotherapy and osteotactic radiosurgery, is called a small field and narrow field. So here I will be talking about the reference dosimetry of conventional fields. This means the field is having sufficient dimension so that the range of secondary electrons produced by the interaction of photons are well within the dimension or boundary of the field, and charge particle equilibrium exists. Now, if we want to talk about the equipment which are the radiotherapy external beam therapy equipment uses this type of beam. So historically we have Cobalt 60 machine, which is still in use in many countries in this part of the world, and it uses field sizes ranging from 5 centimeter by 5 centimeter to 35 centimeter by 35 centimeter. So the field size is defined by this machine is also conventional field. Then we go to the medical electron linear accelerator, where we use X-rays of various energy, starting from 4 MB X-rays, 6 MB X-rays, 10 MB X-rays, 15 MB X-rays, 18 MB X-rays, and even 25 MB X-rays in some countries, not everywhere. The field size here available was 1 centimeter by 1 centimeter to 40 centimeter by 40 centimeter. Later on, few upgradation of these devices took place, and we have multi-modality accelerators available to us. Now we are living in an era where radiotherapy accelerators are having capability of generating both filtered X-ray beams and unfiltered X-ray beams. Very popularly we say double F beam and triple F beam. So I will discuss in detail about these two beams, but their field dimensions will be larger than the definition of narrow or a small photon beam. In case of other equipment for narrow photon beam, probably many of you may be aware, in Cobalt 60 we have a specialized telecobalt machine which is called gamma knife, which was having collimator dimension of 4 millimeter, 8 millimeter, 14 millimeter, 18 millimeter in older versions. Now newer versions have 16 millimeter is the largest dimension of the beam. In case of accelerators, we used to do osteotactic radiosurgery and osteotactic radiotherapy by means of cones. And later on, multi-leaf collimators were also provided capability of defining fine beams for treating a small dimension tumors by the method of osteotactic radiosurgery and osteotactic radiotherapy. Even we have the chromotherapy machine, cyber knife. So these are all examples of the narrow photon tube. This will be discussed by our colleague Professor Rajesh Kincar in detail. So I will be talking about the conventional dosimetry of conventional photon beams only. Now probably all of you might be aware, for conducting the dosimetry of conventional photon beams, we have many protocols available to us. For example, the technical report series 398 published by International Atomic Energy Agency, TG51 of AFM, and similar many other protocols. Even ICRU protocol is available. Then European countries have published many protocols, but the TRS 398 became very popular in many countries, and as per my knowledge, majority of institutions are using this protocol for the dosimetry of conventional fields in their institution. So I just wanted to spend some time here. Now you might have seen the cover photograph of this report many times, but I hope you might have tried to analyze what is the meaning of this cover picture. Here you can see that the center or focus of the physical quantity was absorbed dose to water. So earlier we used to get air karma calibration factor for the ionization chambers, and then we used to convert it to ND air and then to absorb dose to water. So it was requiring the use of certain conversion factors, which was having certain uncertainty associated with it. So people felt that why not to improve the method and develop the standards for absorbed dose to water. So now we have available 4 different primary standards which can give you directly absorbed dose to water from the beams for which we are dealing with. For example, the graphite calorimeter, water calorimeter, chemical dosimeter, and even ion chambers are also available for the dosimetry. Now, this protocol is based on a use of ionization chamber with which is having calibration in terms of absorbed dose to water, and this protocol is useful while doing the dosimetry of KV X-ray, dosimetry of cobalt 60 gamma rays, dosimetry of high energy X-ray, dosimetry of electron beams, dosimetry of proton beams, as well as dosimetry of heavy ions. But personally, I feel that as far as the dosimetry of protons and heavy ions are concerned, further development is required or further improvement in this protocol is required, which is beyond the scope of today's discussion. So now, coming to the topic, first we start with what is the formalism of TRS 398. So TRS 398 is based on the use of ionization chamber for dosimetry of the photon beams. Here we say that we are conducting the dosimetry under the existence of charge particle equilibrium, and the ionization chamber which is going to be used here is also calibrated under the condition of existence of charge particle equilibrium. So I hope all of you are aware what is the meaning of charge particle equilibrium. So I will not discuss this further. As far as the methodology and formalism is concerned, the method says that if one is interested of at a reference depth, I will talk to you what is the meaning of reference depth. This is represented by a symbol capital D WQ, means capital D is absorbed dose to water and Q is the beam quality. and G reference is the reference depth of measurement. So usually when we place ionization chamber for dosimetric measurement, we get reading from the electrometer. This electrometer reading is influenced by many parameters. Some parameters can be controlled by the experimenter and some parameters cannot be controlled. The parameter which can be controlled by the experimenter, for which we need not do any correction, but some parameters for which we cannot control, we need to derive a correction factor for calculating the corrected meter reading of the electrometer. When corrected meter reading of the electrometer is multiplied by observed dose to water calibration coefficient of the ionization chamber and then beam quality correction factor, then you get a value of observed dose to water either in terms of gray per minute in case of cobalt 60 beam or gray per monitor unit or centigrade per monitor unit in case of X-rays from medical electron linear accelerator. Now the NDWQ0, this is a factor. It is called calibration factor in the past. Now it is called calibration coefficient. So this is the observed dose to water calibration of the ionization chamber, which is being used by the user at a beam quality indicated by Q0. The beam quality Q0 is usually cobalt 60 beam, but many standard laboratories, they have a standardized 6 MB X-ray also, which are kept as a standard beam. So we have to see if we are doing the dosimetry with ion chamber which has been calibrated in a cobalt 60 beam and the measurement is done for 6 MB beam, for example, then we require a beam quality correction factor, which is a chamber dependent factor, and it also depends on the quality of the beam for which the dosimetry is done. So I will discuss all these parameters in further details. Usually the beam quality correction factor is measured. Method is given in TRS 398 for a field size of 10 by 10 centimeter. And the calibration factor of ionization chamber is also given by the standard laboratory for a field size of 10 by 10 centimeter. This is just an example of a calibration certificate of an ionization chamber. This calibration certificate is issued by IBA, which is a accredited dosimetry laboratory or a secondary standard dosimetry laboratory, and it is having its measurement traceability with PTB of Germany. Here you can see that observed dose to water NDW is equal to, for this particular chamber, this is the chamber FC65G, 4.797 into 10 to the power 7 gray per coulomb, and this calibration factor has been given at environmental condition of 20 degrees Celsius. The pressure is 101.325 kilopascal, which is equivalent to 1013.25 millibar, and relative of 50%. I have especially brought your attention to these three parameters because this is the influence quantity which influence or affects the magnitude of measurement. So we have to be careful while using this calibration factor for doing the dosimetry calculation after measurement in a given beam. One more important thing I wanted to bring to your notice here. You can see the lab has also quoted the expanded uncertainty U is equal to 2.2%. So this is basically a value quoted at a 2 sigma level or at a coverage factor of 2. This means if I am trying to calculate uncertainty of our measurement, then we have to first convert this value at 1 sigma level or for a coverage factor of 1. So divide this value 2.2%, it will become 1.1% and then use it later. Now quantities, something about influence quantity. I thought before discussing in detail, I will give you a brief overview. What are the influence quantities? So those quantities which are basically not subjected to the measurement, but they affect the quantity for which we are doing the measurement. And these quantities are associated with ionization chamber or the whole dosimetry systems. For example, environmental condition, that is pressure, temperature, and humidity, affects the physical density of the gas which is enclosed inside the cavity, which is used for measurement. So this is the influence quantity. Polarizing voltage applied to collect the charges created by the incoming radiation beam is also one of the influence quantity. There are influence quantities which is associated with the radiation field also. Examples are field dimension or field size, depth of the measurement and the medium, beam quality, dose rate of measurement. So these are the parameters. There are many parameters. These are not the only few parameters. Larger, there are many parameters. Many influence quantities are kept under control, as I said earlier, during calibration of the dosimeter, and your dosimeter is having a calibration factor within that controlled condition. But as I said, we cannot control all the influence quantity. So for those influence quantities which cannot be controlled, we have to calculate a correction factor. Now, for the dosimetry of the reference dosimetry of conventional beam. Now, what I am using reference. This means we are referring certain experimental setup, certain instructions provided by a group of experts or provided by certain protocols, and that's why the name is reference dosimetry, because this dosimetry is referred to a condition which has been provided by a group of people who has worked in this field for many years, and it is the culmination of their experience. So reference conditions are the conditions which provides you insight how to set up the experiment for doing this measurement. For example, it talks about the dosimetry system and what should be their characteristic. It talks about the phantom material or medium in which the measurement will be done. It talks about the measurement condition, positioning of the ionization chamber, field dimension to be used. All these parameters are given here in this table. So for example, phantom material generally recommended is liquid water. Now the question is, why liquid water? Why not solid water? Because solid waters are easily available nowadays to almost all the radiotherapy departments. They are easy to be placed for measurement in a shorter duration. But for your information, I will like to tell you, solid waters are not having a fixed solid phantom materials are not having a fixed density. Density varies from sheet to sheet or different lots of the same material. So that is one source of uncertainty. So we wanted to remove that uncertainty, or we wanted to eliminate uncertainty arising from the use of plastic material. Secondly, the water is available world over in almost similar composition. So if I want to compare my dosimetric measurement with your dosimetric measurement, probably we are on the same footing. So this is another advantage of using liquid water. Here the protocol recommends the use of cylindrical ionization chamber, and the reference depth is recommended 5 centimeter for field for nominal X-ray energy of less than 10 MB, and 10 centimeter for X-ray energy greater than 10 MB. But for the sake of consistency in dosimetry, we usually use 10 centimeter depth invariably for all photon beams, whatever we have in radiotherapy department. Now, as far as the positioning of ion chambers is concerned, the central electrode, that is the central, which defines the central axis of the cylindrical ionization chamber, should be placed at the plane of measurement, that is at 10 centimeter depth. And the measurement depth recommended in this protocol is 10 centimeter in a more general case. Now, here you can see,
एक हफ्ते पहले मतलब एक महीने पे लास्ट में कोविड हो गया।
pardon?
91।
Hello. Okay, I will continue. So now, as far as the setup of the phantom with respect to beam is concerned, it is recommended that one can measure, one can do the measurement by using SSD setup or SAD setup. That is SSD, SAD source to chamber distance, and field size is 10 centimeter by 10 centimeter. This is the experimental setup for SSD type. Here you can see that normal treating distance of the accelerator, which is normally is 100 centimeter in almost all the cases, is placed at the surface of the water. Depth is 10 centimeter, and a cylindrical ionization chamber has been placed in such a fashion that the central electrode is aligned with the depth of 10 centimeter. This is the water phantom, this is a plastic storage tank, you can say, filled with liquid water, and then this ionization chamber, cylindrical ionization chamber, is connected to electrometer, which will give you the reading in terms of coulomb or in terms of even some arbitrary units also, that depends on the manufacturer. Field size recommended is 10 by 10 centimeter. So in SSD, as you are aware, this field size should be projected at the surface of the medium. So here it has been projected at the surface of the medium. So now, for example, one can ask what should be the characteristic or volume of the ionization chamber which could be used here. So IIA TRS 398 recommends that ionization chamber having volume of 0.1 cc to 1 cc can be used for this measurement. This range of the cavity volume has been provided considering a compromise between our intent of measuring dose to a point along the central axis of the beam and sensitivity of the ionization chamber. More generally, we use a ionization chamber which is having a sensitive volume or cavity volume of about 0.5 to 0.6 centimeter cube. So this is almost a mid value between the range recommended by the IAEA. Now, even the measurement can be done even in SAD type of setup, that is isocent, when you are aiming the dose rate or reference dose rate in case of to be used for isocentric setup. The experiment can be designed in such a fashion that you are getting directly the dose rate from the beam in terms of centigrade per mu corresponding to isocentric setup. So here in this case, once again, this is a plastic tank which is filled with liquid water, and we have a cylindrical ionization chamber. It is connected to an electrometer, and then the center of the axis of the ionization chamber is aligned with the depth of 10 centimeter. Now here you may be knowing that in case of isocentric setup, normal treatment distance or isocentric distance of the machine shall be placed at the plane of the interest. So plane of interest is here 10 centimeter down to the surface of the phantom material. So accordingly, the field size shall be projected at 10 by at the plane of measurement. Accordingly, 10 by 10 centimeter field has been projected at the plane of measurement, that is 10 centimeters. So this is a slight difference between SSD setup and SED type of setup. Otherwise, measurement approaches, calculation approaches, everything are similar. Now we have to determine influence quantity. As I told you, temperature and pressure, though we maintain a air conditioned room, but still there are temperature variations. So we have to note down the temperature in the beginning and temperature at the end of the measurement. Sometimes even it is recommended to place a thermometer, a sensitive thermometer, inside the water tank itself, so that it gives you the temperature of the water. But even if it is not possible, if you are measuring the temperature of the room, probably it is not far away from the condition for which you require that value of temperature and pressure. So here what we do, we record the temperature in the beginning, which is called initial temperature, and at the end, which is called final temperature. Then we calculate an average value of this temperature, which is taken as temperature T, and then the T0 is the temperature given in the calibration certificate of the ionization chamber, which you have seen it was given as 20 degrees Celsius. P0 is the reference pressure or pressure used or pressure at which the calibration coefficient of the ionization chamber has been expressed, and the P is the average value of the pressure in the room measured during the experiment, in the beginning of the experiment and at the end of the experiment. So if you put all these values in this expression, you will be able to get a correction factor which is called temperature pressure correction factor. The value of the reference pressure is 1013.2 millibar. In older units, as we still we use this unit, or in case of SI unit, it is 101.3 kilopascal. Now, second influence quantity is polarity correction. Some of the ionization chambers, they are having polarity dependent response. Polarity dependent response means if you are operating the ionization chamber, say for example, plus 300 volt, it will give you some meter reading. But if you repeat the same measurement by just changing the polarity to minus 300 volt, you may not be able to get the same value. So in that case, we say that this ionization chamber is having polarity dependent response, or the sensitivity of the measurement of ion chamber depends on the polarizing voltage. If this is the case, nowadays the manufacturer has taken a good care while designing the ionization chamber which is used in radiotherapy. The magnitude of polarity dependence is drastically improved, and hardly any chamber is having polarity dependence for photon beam, except plain parallel chambers which are used for electron beam, which I am not going to discuss here. So if by the way you assume that you are using a ion chamber which is having slight polarity dependent response, in that case we need to determine the polarity correction factor. So IAEA TRS 398 recommends the use of two voltage method. Use of positive and negative polarity, and take the average value of these two and calculate this correction factor by this expression. So for example, what we have to say, for example, if a ion chamber is having is generally used for 300 volt, initially you apply a voltage of plus 300 volt and get it settled, or try to get electronic equilibrium of the electrometer. Take measurement or readings in the similar setup, whatever we have shown earlier, either in SSD setup or SAD setup, as per the choice of the user, and then change the polarity to minus 300 volt. Give some time to the electronics of the electrometer to get stabilized with the changed polarity, and take accordingly few more readings and take average value. So now these two values, M plus, use its absolute value. Whether the reading displayed by the electrometer is positive or negative, do not worry about it. Take its absolute value and divide this sum by twice of the reading taken at positive polarity, if you are going to use the positive polarity for further measurement, or twice of the reading of taken at negative polarity if you are going to use this chamber further for at negative polarity. So this way one can calculate the polarity correction factor. Now the third and last polarity correction influence quantity which we generally try to find out is correction factor for recombination loss, or sometimes it is also called saturation correction factor. So this is to account for loss of ions created in the cavity of the ion chamber due to the recombination of ions, and this can be calculated by determined by two voltage methods. So here you have to apply a normal working potential, polarizing potential to the ionization chamber, and another potential which should be either half, but more generally and ideally 1/3 or more than 1/3 of the normal operating polarizing voltage of the ionization chamber. And then if you have acquired the reading at voltage V1, which is the normal operating potential of the ion chamber, and reading M2, which is at reduced polarity of the ion chamber, then if you put this reading here in this expression, then you will be able to get a correction factor which is called correction for recombination loss of ions or saturation correction factor. A0, A1 and A2 are the constants. Its magnitude of these values of these constants are dependent on the type of beam. Their values for continuous beams are different, pulsed beams are different, and pulsed scan beams are also slightly different. But nowadays, almost all or majority of the accelerators, whatever we are using in radiotherapy, they are generating pulsed beam. So we will look for a table where values of A0, A1, A2 are available for pulsed beam. This is the value I have just noted from the TRS 398. The voltage ratio of 2 or 2.5, 3, 3.5, 4 and 5. These values of the A0, A1, A2 are given. More generally, if you can see my earlier example, I have taken, for example, the operating potential V1 is 300 volts and the potential V2 is 100 volts. So here, if I take the ratio 300 by 100, this ratio work out to be 3. So now I will refer the fourth row of this table, the ratio of V1, V2 and corresponding values of A0, A1, A2 will be used in that X quadratic equation for calculating the value of saturation correction factor. So now when we use this value to the meter reading taken either in SSD setup or SAD setup, you are getting a corrected meter reading. So now we are having with us corrected meter reading. Next meter reading will next value was the calibration factor of the ion chamber, which has been given to you by the standard laboratory. So last parameter for calculating the absorbed dose at reference depth we wanted is measurement of beam quality correction factor. For this purpose, you have to once again do another experiment. But the experimental setups are not much different. Here we are going to use the SAD type of setup and we will be acquiring the reading site, the depth of 10 centimeter and depth of 20 centimeter, and probably majority of you might be aware this is called tissue phantom ratio 2010. So here the reference conditions are this phantom material is the same liquid water. We will be using cylindrical ionization chamber because it is already available in experimental setup. PP chamber can also be used, but why to change the chamber later on. Then all other things, I hope I will not spend much time here. Field size, the field size projected at the measurement plane is 10 centimeter by 10 centimeter. This means if I am taking the reading at 10 centimeter depth, field size projected at that depth is 10 centimeter by 10 centimeter. If I will be taking reading at 20 centimeter, field size projected at the plane of measurement will once again 10 by 10 centimeter because this is isocentric setup. So this is the figure I have taken from IAEA report. Here you can see this is the experimental setup for measurement at 10 centimeter. This is the ionization chamber and we are having electrometer and all. This is the beam. So irradiate the ion chamber in this condition, take at least few readings to have a good statistics and calculate average. Now fill this phantom with 10 centimeter water. And then your ion chamber is located at a depth of 20 centimeter. So take few readings in this situation, take the average value. So now you are having the meter reading at 10 centimeter as well as at 20 centimeter, and this meter reading needs to be corrected for the temperature pressure correction factor also. So when you take the ratio of these two, you will be getting a factor which is called beam quality correction factor. Beam quality correction factor for high energy X-rays are in the range of 0.6 to 0.75 in the range 4 MB to 15 MB, but it can be even higher if you go for higher energy. So the values of the beam quality correction factor, as I said earlier, is a chamber dependent factor as well as it is radiation beam dependent factor. So the calculated Monte Carlo calculated values of this factor against the beam quality of X-ray have been tabulated in TRS 398 for large number of ionization chambers. I have just taken a small rows of the tables from the ion chamber from different vendors. For example, I have taken value for Capintech PR05 mini ionization chamber. You can see the values at beam quality 0.62, 0.65, 0.68 are available up to 0.74. By the way, it may happen sometimes that your values is not exactly 0.65 or 6 MB X-ray, for example. Then you have to interpolate the correction factor between these two values, 0.65 and 0.68, to get the exact value of the beam quality correction factor for your ion chamber. So now, once you put all the numerical values of the meter reading, the calibration factor and beam quality correction factor, you will be able to get absorbed dose to water at the reference depth. And if we have used the value taken in case of SSD type of measurement, usually right here, this is the value derived from the SSD type of setup. So this will be called dose rate at the reference depth or SSD type of setup. Now, more generally, or traditionally, we try to present this value at the depth of dose maximum, that is at G max. So here you can convert this by use of a percentage depth dose, because majority of you might be aware that percentage depth dose is a parameter which is generally used for SSD type of setup for converting the dose from one depth to another depth. So now here we have used the experimental setup where the depth of measurement was 10 centimeter, field size was 10 by 10, SSD was 100 centimeter, and say for example, if we have used 6 MV X-rays for irradiating ion chamber, then in this case, if you use this expression and the value of percentage depth dose, you will get dose at the depth, dose observed dose at the depth of dose maximum. If say, by the way, you require this value to be converted to observed dose suitable for use in SAD type of setup, but you do not have done the measurement by creating experimental setup corresponding to SAD types of setup. So in that case, now you might be aware, if we are doing a small changes in distance with respect to the position of the source and the phantom, this change is taking place in air only. So then there is no harm in using a inverse square correction factor for 6 MV X-ray, which is having a depth of dose maximum of about 1.5 centimeter. The inverse square correction factor can be calculated using this relation. So if you use this correction factor in the absorbed dose to water and the depth of dose maximum in case of SAD setup, you will get it converted to SAD setup. If by the way you have done the direct measurement creating a setup for SAD, it is well and good, but still this method can also be used. So now the final item I wanted to discuss is, whenever we do dosimetry measurement, it will be felt or it will be thought incomplete if you do not express the uncertainty in your measurement, and it has also been given in the TRS 398. So usually we try to find out two different components of the uncertainty. One is type A component of the uncertainty, which is a statistical in nature, and type B uncertainty, which is non-statistical in nature. So I would like to refer all of you to refer IAEA Tech Doc 1585, which gives in a very simple term what are the type A and type B uncertainties, how to calculate it, and if you want to have further details, refer ISO booklet, ISO GUM usually we say. The calculation of type A uncertainty, as I said, is a statistical in nature. So if you increase the number of readings taken for a given situation, probably you are trying to minimize the uncertainty due to type A. And type B uncertainty is fixed because it is associated with the characteristic of the equipment, your fixed dimensions in the phantom material. So you have to just simply get the value from literature or from your own experience while doing the experimental setup. And all these, well, one thing I wanted to tell here, which is you can take as a caution. Whenever you are taking the value from the published data or given in brochure of the manufacturer, make sure that whether this value is quoted at coverage factor of 2 or coverage factor of 1. If it is quoted at coverage factor of 2, convert to at coverage factor of 1 and sum up all type A uncertainties in quadrature and all type B uncertainties in quadrature, and when you sum the resultant values of type A and type B uncertainties together, you will get a value of combined uncertainty, and combined uncertainty usually be expressed at 2 sigma level or at a coverage value of 2. So multiply that value by a factor of 2, you will get the exact measurement uncertainty, which should be expressed along with your measured reference dose rate for given X-ray beam. So I think this was everything of my talk as far as the summary of this talk is concerned. The IATRS 398 is basically a protocol which is based on the use of ionization chamber, which is having calibration in terms of observed dose to water, and this calibration is more generally against a covert 6 beam. So whenever we are doing measurement at other beam quality, correction factor has to be determined, but nothing is described in case of departure from the reference condition. So this may be a small shortcomings of the IATRS 398. Further, reference conditions has not been mentioned in case of a special radiotherapy equipment like gamma knife, cyber knife, tomotherapy. So this means it was requiring another methodology or instructions. So this is advantages and shortcomings of IATRS 398, but it is a very useful protocol. It is used worldwide. It is very simple to use and to be implemented in the practice, day-to-day practice. So with this, I thank you all for your patience listening. And now this talk is open for the discussion.
Thank you, Professor Dr. S.V. Sharma, for excellent talk and elaborating on reference dosimetry of the conventional photon beams. You have spoken about the importance of reference dosimetry, TRS 98, and the field sizes what we use, and what are the influencing quantities and how to correct all those things. So very nicely explained. However, there are few questions which have been put to you, and just I will try to get answer for our participants, very active participants. How uncertainties in chamber calibration are measured? That is the first question.
Okay. So uncertainty in chamber calibration, I thought they are talking about the uncertainty in chamber calibration at a standard laboratory. So there they find out uncertainty, a statistical part of the uncertainty, that is type A, because they also take a lot of readings, and the standard deviation is used for calculating type A uncertainty, and the uncertainty associated with the stability of the electrometer, uncertainty associated with a small error in the experimental setup, all are combined together, and they quote a standard uncertainty at a coverage factor of 2 in their calibration certificate.
So they are different from the influencing quantities like pressure, temperature corrections. They are different with the equipment and with the setup. So another question is that why only cylindrical chamber is recommended for high energy photon beam, and what are the issues with a parallel plate chamber?
Yes, cylindrical chamber, I will tell you, it is handy to use. Even parallel plate chamber can also be used, but parallel plate chambers are specifically required in case of electron beams of energy less than 10 MeV. Reason I will tell you, there is a phenomena called inner scattering and outer scattering. So in case of cylindrical chamber, in case of photon beam, this phenomena is not significant. So whether one uses cylindrical chamber or parallel plate chamber, I don't think there will be any difference or any significant difference in the measured value. But it is historically used. People are familiar, so they use it very popularly. And as far as the PP chamber is concerned, earlier versions of the PP chamber was having a lot of problem with inner scattering phenomena. When say, for example, if it is electron beams of lower energies are used, and if polarizing potential of 300 volt is used, so now you see that we are applying a positive polarizing potential. This means electron will be attracted by the applied voltage. So electrons which are not supposed to contribute in the ionization in the cavity, or some of electrons were contributing. And if similarly, if you use negative polarity, some of the electrons which were supposed to contribute in ionization process were pushed out. So this was the problem with plain parallel chambers. Because of that, they are not very popular in use, and the cylindrical chambers are very popular.
Now the question is about the polarity. Some of the delegates asked why the polarity is minus 300 or plus 300 volts is used. What is the reason?
Yes, this is the recommendation of the manufacturer. Say, for example, if a manufacturer has designed the ionization chamber, and if they usually plot a curve, the response versus applied voltage. So they get a plateau. Center of the plateau is recommended as the actual polarizing potential for which this ion chamber should be operated. So this value is quoted by the manufacturer. It is not the decision of the user.
So very excellent questions were there. And another question was why the depth, reference depth is 10 centimeter in water phantom. Why not more or why not less?
Yes.
Participant has already answered, but we want to listen from you.
Yeah. So now this is a very logical. This question has two components. One is clinical. 10 centimeter is thought to be clinically relevant depth. This is one part. Second part is when earlier we used to do this measurement at the depth of dose maximum. So I hope majority of our colleagues who are attending here, they know that there is a phenomena of contribution of contaminated radiation. Low energy photons generated by the collimator system and secondary electrons generated in the collimator system monitor chambers, they are able to penetrate up to the depth of dose maximum. So their contribution were counted. So, but when we are treating a patient having a tumor at depth of 7 centimeters, their contributions were not available. This means we were doing overestimation in reference dosimetry, but during calculation that was not the case. So there was a debate world over what should be the ideal reference depth. So you might have seen that IAEA has also recommended either 5 centimeter or 10 centimeter, the choice of the user. So beyond 10 centimeter, I don't feel it is logical from clinical point of view. And above 10 centimeter, there are some physical uncertainties from the radiation beam. Because of that, a single value for having consistency world over has been selected.
In reference to this, another question is there. Can we use TPR at 15 centimeter and 25 centimeter as a beam quality index for photon beams?
Yes, any depth can be used, but we do not have the value of beam quality correction factor against that TPR. If world has been recommended that TPR 25 by 15 and KQ values are available, fine. If somebody is able to calculate the KQ value corresponding to that TPR 25 by 15, it is well and good. That in principle there is no problem, but 25 centimeter is once again at the exit surface of the patient. It does not have much relevance. So considering that 20 by 10 is more logical.
There are many questions, but I will put this last question to you, and then because we have to move further. If our chamber was calibrated with photon 6 and 10 MV, how to get the conversion value for electron beam?
Conversion value for electron beam, I don't think the calibration coefficient obtained at 10 MV or 6 MV should be used for electron beam. One has to go for cross calibration using this chamber. So there is no other approach. Otherwise, you are incorporating unwanted uncertainty in your measurement.
So there are many questions, but we'll leave that we can send them by email or something, questions and this thing. So thank you, Professor Dr. S.D. Sharma, for an excellent talk, the discussions and answering the questions. Despite of away from Mumbai, you have done it. Thanks to you, from me and from AFOMP, all AFOMP members and the EXCOM for making it to happen, this AFOMP first webinar, and that too from you. Thanks you very much. Now the floor I am handing over to you to introduce the next speaker, Professor Rajesh Kincar, and the topic and the conduct entire the webinar, and then finally you can hand over back to me for my concluding remarks. So over to Dr. S.D. Sharma for introducing the next speaker and continuing this webinar.
Thank you, sir. Thank you very much. I thank all the participants as well as to you and the AFOMP for giving us this opportunity. I will now introduce my colleague, Dr. Rajesh Kincar. So, Dr. Rajesh Kincar, I hope I have some problem in opening his slide. Dr. Rajesh Kincar is my close colleague in Tata Memorial Hospital. Many a time we work together, and he is currently professor and head of medical physics department. He has a very long experience of working as a clinical medical physicist from 93 onwards, almost 24 years of experience. He has published a number of papers in many reputed journals, and he is teacher of our 1-year post-MSc diploma in radiological physics program from many years. So Dr. Kincar is a person who is directly dealing every morning, every evening with radiotherapy beams, and he will talk about the reference dosimetry of a small photon fields. And he has a lot of experience in this work, and he has published a few papers in dosimetry of small photon beams also. So now I invite Professor Rajesh Kincar to please take over the window and start your presentation.
Thank you, sir. I hope I'm audible and visible as well.
Hello.
Yes, yes.
Yes, okay. And also, as Dr. Chogule has mentioned, probably the light is now fair enough to see me. Okay, so I thanks again the AFOMP, the MP, the dignitaries, the students, my teachers, and specifically the IT team who must be helping you and all of us. That is the tremendous support in these days the IT has given us. Now I would share my presentation to you.
Yes, it's visible. You can go to the PPT mode. The presentation mode you can go.
Yes, I'm going. I think now it is visible.
Yeah, excellent, excellent.
Thank you so much. Thank you so much. Okay, so couple of my thanks as over, and thank you, Dr. S.D. Sharma, for my kind introduction as well. And sir has finished in a perfect manner, and that has given me definitely a burden that I must finish on time as well. Okay, so quickly moving to my presentation, the topic is about reference dosimetry for small static fields. And this is basically, you can see on the screen, is two literatures which are available. My earnest request to everyone, though a fresher, though experienced, don't leave the reading. So go through TRS 398, read 483 and the uncertainty documents and the literatures line by line. I think it is very useful. Many things which we had questions, your questions will be answered in those slides as well. Can I see? Can I see my presentation? Can you see the next slide now?
Yeah. Background.
Thank you,
background.
thank you. At any moment, if you are not able to see my slide, just let me know. Okay. So my presentation, basically, I have covered in two major topics. One is basically a very background. I will be touching to the TRS 483 and showing some of the factors, some of the pages which are in the TRS 483, and then moving to our work, what we did in the linear oscillator, which we called it as a conventional linear oscillator. And also we will be moving to our measurements and the scientific work, which we carried in an unconventional LINAC or non-traditional LINAC, so-called tomotherapy. Okay, so if you see the background is already been covered, we know the 3RS398 and TG51 refer to the primary dosimetry lab, and they have the departures from the reference condition. If so, then it becomes a difficulty in the conventional fields as such. We all know, I will just quickly tell you, the small field, you must have read many papers, many literatures and heard about it. So thumb rule, the field size which is lesser than 4 cm by 4 cm, having the lateral charge particle range of the photons, and which will contribute to the dose. Now, this is basically the important component. It depends on the range of the secondary electrons which are generated in the medium after interaction. And in a broad beam, they have negligible impact because they get enough isotropic area or volume to scatter and deposit their ionization. Same is not the case in the narrow photon field, and we all know whatever is being interacted, which may exit and which may not be able to sufficiently collected by a volume of so-called detector, which we will be using into the work. So the small fields in external radiotherapy has definitely been widely used now. If you see the last couple of years or 5 years or 10 years on the line, it has been mostly used in the clinic. It is created by downstream from the collimation of flattened or unflattened beam if you have in your machines. And the different collimation types are, as you are aware, they may be jaws, they may be multi-leaf collimators, the cones, stereotactic cones, or the tertiary collimators, which are mounted or maybe in-house on the collimator head. So these small photons particularly will have issues in the lateral dimensions, which cause the penumbral effect. And I particularly insist on this penumbral effect because you all clinical physicists or maybe students must be working with a planning system which has an algorithm and which has to be acquired a particular beam data with a particular penumbral data along the field axis and at the off axis as well. So particular detectors and the radiation field size are quite important. So definitely the narrow fields are quite used, and the precision radiotherapy is basically a technology driven, and the small fields requirement are more and more in the department now. So the small fields are definitely used in early stage cancer diagnosis for technology developments and the machines which are capable to deliver those, which definitely gives a high dose conformity and which ultimately gives you the normal tissue sparing. Having said that, yes, we need to understand the subject in detail, understand every component which you will be using in the small field dosimetry and as a team, and then get an experience on the conventional or a broad beam, and then move to the smaller and smaller field dosimetry. So use of small fields is definitely a challenge, which has definitely weakened traceability, as Dr. Sharma has mentioned, to the reference dosimetry. There would have been reported dosimetric errors which are larger and larger in quantities. And of course, and these are challenges sometimes may discourage us to implement a small field dosimetry program in the department. However, now the literatures are available and the teams are available, people are there nationally, internationally, and e-access of the literature is also available. So don't get discouraged and start somewhere. So one of the incident, which was basically a physicist did not understand, and the out factor calibration in the TPS probably was not taken into account, and the incident happened, and it is to be taken as a caution. Is it a time now to move to the paradigm shift of the dosimetry protocol? And yes, with the experience of the conventional procedures, with the teamwork, with the literatures and the equipments, we must move to develop the standard guidance for the dosimetry, we must take help of IEA, and this with the help of IEA and APM, when they started to work on a group to form the code of practice for small field dosimetry. And then finally now in last 2018 or 19, the TRS 483 was published for us. So these code of practice, they definitely say for formalism, which will move to the new terminologies in this code. They say the machine specific reference field, where we can't move to close to your reference conditions. And then the plan class specific reference field. Why it has come this new word, maybe for the new to the students? Yes, we are always working with the treatment planning system, and your plan class specific reference field may be different from your conventional beam approaches as well. As I already mentioned, these two documents can be very well read and understood before using it into the equipment. So coming to the dosimetry equipment. Now this, I'm basically touching the TRS 483 very systematically given and putting the summary or the condensed matter to you so that you can at least understand and then read in detail. So I will be using now MSR word wherever it is coming as a machine specific reference field. And this MSR field, it is advised to use an ion chamber. We know it is a backbone, a reference one, and we know the advantages of those ion chambers as well. It needs to maintain the lateral charge particle equilibrium, which has been already explained. And then we need to see the approach where we have to obtain the calibration coefficient directly in the MSR field. The second approach, definitely the ion chamber, if it is calibrated for current standard reference condition, we need to correct the factors to convert into the MSR field to avoid the volume averaging effect. Of course, the ion chambers are not the only benchmark. They have their said uncertainties or the challenges. One is the volume averaging. We all are using the reference ion chamber as 0.6 cc or close to that. And as you go down to the miniature volume chambers and the field is going to be a small, there is going to be volume averaging effect. You will find out many literatures from APM and IEA and other protocols on volume averaging effects in medical physics and peer-reviewed journals as well. Now, there need to be necessary corrections, either become excessively large and uncertainties has to be estimated. And I will show in my presentation a detail the uncertainty estimation among the two machines. Definitely, we must not forget about the spectra of the beam, which changes the beam quality and then which change in the field size as it is variable. The question was there in that Dr. Sharma has already mentioned that the water or solid water, or real water or PMMA, etc. We come to know all these words and we hear these words. What should we use? Yes, definitely. For some treatment units in your clinic, use of water phantom may restrict you. Definitely in that case, we can use the plastic water substitute. Today, these are the terms which are used. These are the manufacturers or the material used, and they are supplied by the vendors which are nationally and internationally accepted by the community. And many of you must be having in your department as well. So this code will give you the methodology to use the plastic water substitute as a water phantom in the department. Now this code of practice also tells about the reference dosimetry moving to the smaller one, and we must understand the reference field dosimetry down to the MSR field. While you refer this small field dosimetry book or the document, few components are very excellently explained. They are repeated in some of the chapters, but they are very important to understand and keep the link between the previous chapters and the post chapters as well. So field size, rectangular or circular. So it is definitely not unique. It may be different in your case. Each dimension will be defined. Somewhere we need to come to a common platform where we should report all our results. And the FWHM we must have heard earlier, and it is very common, but now there is a time to use this word and the terminology into your clinic as a full width at half maximum. I will just quickly brief about the field size definition. We all know, but quickly just for the students, I will review it, the geometrical field size and the irradiation field size. So this one is defined as the projection of the collimator of the radiation source on a plane perpendicular to the axis of the beam. This will correspond to the aligned light field which will corresponds or equals to the collimator setting for focused flat edge collimator, so-called what we are using it. The irradiation field size, which will be defined in terms of the dimensions of the area in a plane perpendicular to the radiation beam axis, specified by the isodose line. Here is basically the irradiation component come, and then isodose line will come in the picture. Again, the definition of the field size in the broad beam and the small fields, I'll just quickly tell you about. The 50% is always referred as a field size or the FWHM. In the smaller fields, as the field size specified at 50% related to those level, it becomes broader, and then apparent field size widening is opened. So for a given SDT, the effect is dependent on the source to collimator distance, which is very important, and they are variable in the different treatment machines as such. So this MWHM, it is advised that it should be used for selecting a detector perturbation as a function of field size. I will show in my subsliding the slides. And it is also concluded in the code of practice that this WHM of a lateral beam profile is most represented, an essential parameter to accurately quantify the small field dosimetry for your experiments. The beam quality, a very important parameter, already Dr. Sharma has mentioned. It can be defined by two different protocols, by IA as the TPR and percent detectors at 10 centimeter. I need not explain much in detail. And this beam code of practice tells you how to convert these indices from MSR field to a conventional field size. Because as we go down in the MSR field, the literatures, the correction factors are all not available, and we suddenly get stopped that how should I proceed and to whom we should ask. Definitely many modern Linux are coming with the FFF technology, and they are also mentioned in the code of practice. Two slides I will be just showing quickly on the hardening of the energy spectrum. Just understand that as the field is shortened or the condensed, the beam energy spectrum changes and the beam is hardened and hardened. So the reasons are mentioned in the shield, the photons which are scattered from the different components inside the LINAC head. Number of low energy photons are scattered. For the off-axis fields, definitely the case is different. There will be an increased relative contribution of the photons which are scattered. And then additionally, the amount of photon phantom scatter will also decrease, which will be difficult to understand and then use it into the beam. So this hardening, these two effects will result in hardening of the photon spectrum at any point on the beam axis. Ultimately, you must have heard about the mass energy absorption coefficient, which is water and the detector material, which will also correlate to the potential change in the stopping power ratio. This is a common terminology which we read from the TRX 398 between water and the detector, because the mediums are slightly different. The detector composition, particularly the central electrode where it is the charge collection is maximum, it will impact and more in the small fields where the recombination and the collection is very, very crucial. So this increasing of the mean energy, electron energy also is observed in a couple of papers, which can also affect the stopping power ratio. And I must say that this stopping power ratio or parameter is very important in the high LET radiation, so-called proton and carbon ion. So definitely we are not going to touch those, but just to mention it. Now the field of two factors. Question is it a reference measurement? I will not be covering it. Next speaker is going to cover it, but owing to this difficulty of measurement, the code gives you the option to move away from the reference condition to a methodology to determine the field output factors. And the determination also is formerly as a reference dosimetry, is treated as a reference dosimetry as such, but I will not be covering in my lecture as such. So the small field conditions, if you read the TRS 483, there are three conditions mentioned. Out of these three, at least one of the following three physical quantity conditions, if they are fulfilled, then you can say that field is a small. This graph is known to you in your curriculum when you underwent the curriculum and the study. And brief summary of this figure is basically the loss of lateral charge particle equilibrium on the beam axis. So where it is for every energy, if it is same, the dose to karma and the air karma simulated by the Monte Carlo simulation, you can use this condition in your measurement. So that field is supposed to be a small field. Next is basically the partial occlusion. We know that the source is blocked. In LINAC, it is a target or the focal spot from where the radiation is exiting, the beam is exiting. And then when it comes for a narrow beam or a wider beam, it has not a miniature significant impact, but however, yes, it has the impact on the lateral penumbra issues, which are crucial in the field. Third parameter in the small field condition is the size of the detector. So first two parameters were the beam related. The third parameter, this one, is a detector related. As you start deviating from using the reference class detector, moving to the small field or miniature volume detector, you see that there is some effect like what we call it as a virtual source distance or similar to that, that probably the beam exit point is different because of the source occlusion. And these two effects will definitely create challenges. And for these reasons, we can see the small beam conditions, field conditions are assumed to exist when the external edge of the detector volume is at a distance from the field edge smaller than the LCP. I will show you in a particular my slide that a particular detector, how to confirm that it is suitable for the measurements. So a particular detector will have volume averaging, we already said that. And if there is a deviation from Bragg cavity theory, definitely we will not be able to measure. And this intermittently give you the larger uncertainty because of the fluence perturbation, because of the detector, because of the medium, or so on. So in 2017, we, without probably any knowledge of the accurate documentation, perfect methodology, we had measurement of the total scatter factor, which usually any clinical institutions we do, and we did with for the small holes for the SRS and with the plastic scintillator detector with the help of the vendor, and we concluded that yes, those factors were within 5% or so compared to the literatures from IROC or maybe MD Anderson centers, etc. However, we should also mention that this time, definitely we did not have an 100% knowledge that what should be the uncertainty and what should be the care taken into the small field dosimetry. Now, we'll go back to the title slide of this, reference dosimetry for small static photon fields. And let us move from the right to left. If you say static photon fields, I have no issues and challenges. Lecture 1 has already told it. We have no uncertainty and we are comfortable in this. As I club one more word as a small static photon fields, then the challenge starts. Uncertainty starts magnifying. If I club 2-3 more words, I need to do a dosimetry, that to a reference one, then it becomes this picture. I don't have a clear vision and I must break this wall. The breaking of this wall is not so easy. You need to understand the topic. You must have the adequate equipments so as to you hit the arrow to the perfect target, and hence it becomes more challenging and the associated issues with the larger uncertainties. The beam quality is also one of the important parameter, as already has mentioned. The few questions come in our mind. Is the beam quality specification for the conventional 10 by 10 reference field appropriate? Is it sufficient for the dosimetry of smaller field? Answer is yes. Very small variation of the water to stopping power ratio with the field size suggests that an ion chamber or detector, the beam quality index would be sufficient for the field sizes. Variation are basically minimum, but they are field dependent output factors which can be corrected. Second question comes into mind is how can the beam quality index be determined from the radiation generators which cannot establish the conventional reference condition prescribed for the measurement of the beam quality? What is the answer? There are various approaches mentioned in the Code of Practice and TRS 483, and few are mentioned very clearly. Alfonso et al. Has introduced the concept of machine specific reference field, or the another one for tomotherapy machines also introduced for the specific beam quality index particular to the percentage of dose, and the measurement of TPI 2010 in clinical field, set field with the ratio of different doses at water and converting into a reference beam quality. Now the detector response, how does it contribute to all those? Yes, its size, shape, material in the detector, as I mentioned, and the material in the detector means the central electrode. Sometimes it may be high Z, low Z. And particular example I wish to mention here is the current latest diamond detector. Vendor will give you the 3 or 4 types of diamond detectors, and particularly every detector will have different composition of the collecting point as a high Z material, and the density varies, and that collection will give an uncertainty or the perturbation. The wall of the material, central electrode, electron in the scattering effect, and volume of the medium which is being displayed by the detector. Now, the energy range of the interest is also very important. Like the question must be coming into the entry level or the debutant medical physicists who are in the clinic. I'm doing a rapid plan, IMRT plan with 6 MV. I've been told not to use a 10 MV. What is the reason? Is it a thumb rule? Is it an evidence-based, or is it of no use? Then why we buy a linear oscillator with higher and higher energies in the field when I'm not using it for my high precision radiotherapy? Of course, the basic reason would be same. We all know that they have the effect on the greater depth rather than the shallow depths. They also have associated lateral electron range, which may increase the penumbral impact, and more than 10 MV, another aspect comes as a neutron contribution from the beam. But this is particularly noticeable for small field sizes and within low density tissues, such as the lung in the clinical planning. And that's why it is need to be recorded and taken care. If you refer to some of the literatures, they also have mentioned about this. So if you see the ICRU report and the IROC, the Houston MD Anderson Center, they do the quality audits for national and international centers. You can see the most of the reports they got from this is used by 6 MV, almost 96% of the beam, while the 3 to 4% of the contribution goes to the 10 MV. So it is definitely one needs to have a look at what is basically the point where it gives a scatter contribution at a lateral depths. The parameters which we need to understand for the small field dosimetry, which already has been spoken about, and sometimes it may come repeating. So my apologies for that, but it needs to be kept in the slides to understand the continuity. So what are the non-conventional beams or machines? They are tomotherapy. What are the parameters are mentioned? The 5 by 10 centimeter is supposed to be recommended at a distance of 85 centimeter. Why 85? It is the isocenter so-called, or the bore diameter of the machine. And the rest of the factors are mentioned in the machine. The cyber knife is basically the largest fixed collimator, which is defined as a reference field. The field size is defined at 80 centimeter, and any of the parameters can be taken. Gamma knife is already mentioned about this, the special case machine, which will be the maximum field size diameter is taken as 1.8 centimeter or 1.6 centimeter, depending on the machine model which you have. Many institutions and centers still might be using the Brain Lab add-ons collimator, and reference again, it is going to be 10 by 10, and which is probably used. Now, let us pay attention to this slide. What is basically TRS 483? Is it complicated? No. If you read page and page and understand what it is mentioning, what is saying to me. Dr. H.D. Sharma has already mentioned about a standard formalism, meter reading and the absorbed dose calibration or the sensitivity correction, and then in a nominal scenario. If I'm moving from the nominal scenario to the uncommon scenario, I must use the beam quality. It may be referred to the cobalt 60, or it may be referred to the energy which you are going to use it. And accordingly, the abbreviations are being used. So read those abbreviations and don't get afraid of these bigger and bigger formulas. They are not very new. They are not a rocket science. They are very understandable, and see how they are going to imply in your measurements. So if you see the reference dosimetry, the machine specific reference fields, we already have seen how they are mentioned. If this NDW is given by this quality correction factor, you can imply to these fields. And the third approach, which you are going to the hypothetical reference field, so-called the MSR, close to the reference field, can be used if you apply the correct quality correction factors. I will tell you in my next slides. So these MSR fields for common radiotherapy machines, which already has been discussed in detail, and they are quickly brief. I have taken it from TRS 483, and the equipments which for the machine specific reference field, they are ion chambers. They can be used as a phantom. You need some electrometers, you need some check devices, and then you need some thermometer and barometer if when you are doing a reference dosimetry. What are the ion chamber and all? Yes, the ion chambers are basically the water equivalent. They don't perturb the radiation fluence, and they have many other advantages. I'm not going to into detail. We are day-to-day using it. The thimble ion chambers have been proven to be robust, simple to use, suitable for clinical reference dosimetry in MSR fields in water as well as in solid water phantoms. The desirable conditions for these fields are basically the chamber needs to be aligned and other factors as such, and so that it gets into the normal charge particle equilibrium conditions. So what are the generic conditions? If you see here, the double F and the triple F beam, the mention is that what chamber volume are suitable and they are used. And we all know that in flattening filter beams, we have 0.66 chambers which are already being used. And for unflattened beams, typical volume chambers are recommended as 0.1 to 0.3 cc if you are going toward the small fields. So if you see the characteristics of the beam, when we go to the MSR field for the field size of 6 by 6 equivalent, there are list of the chambers which can be used. The dimensions are given, their composition are given, and they are very useful to find out that whether they are suitable to use in your clinic or not. So I will just quickly go to the next slides, and they are explicitly explained into the their composition, etc. Now, when the field size is less than 6 centimeter and 6 centimeter, the conditions changes. The 6 MV beams between 3 to 5 centimeter, definitely LCP exists, but the farmer type chamber is too large for such a field. And dosimetry under these circumstances would result in an underestimation of the absorbed dose to water on the central axis because of the volume averaging other effects. So be cautious not to use the FC65 chamber. And these are the few chambers are listed here, their composition when your field sizes is less than 6 centimeter by 6 centimeter. Quickly, I will highlight one of the slide here and emphasize on the leakage of a particular detector, how you should estimate, measure it, the leakage for 3 to 5 minutes and convert into a minute. And the recommendation is suggested that it should be smaller than 0.1% of the chamber reading, and see that you may use a different combinations, only chamber to the electrometer, only chamber and cable, and then see that what is the variable into the compound. Phantoms, of course, we all know the water is recommended, but there are the solid water phantoms are also mentioned, and the elemental composition is very, very important, and it is basically fraction by weight, the density, mean atomic number, and the manufacturer must provide you the data sheet where the density is clearly mentioned in the slide. Now the phantoms and chamber sleeves, there may be a situation where you may not have an adapter. You want to put your detector into a water tank. You need to use some sheets, probably sleeves. And it also has been mentioned that the sleeves will be probably sometimes made up of PMMA, preferably not thicker than 1 mm or so. It has also been reported in the literature that they use some different powder coating or something, but definitely it will affect your beam fluence in the beam. So that is important that you must take into account the care. The plastic water substitute phantoms, they are definitely very important, and it advised that the procedure to be followed, a very systematic procedure to maintain the measurement depth into the factor. So for these reference condition, I am not going into the detail, it's already been covered, that reference depth of the measurement and other things for the different machines. This slide will quickly give you the glance view of what material is being used for different machines. and what are the parameters, what is the measurement depth, what is the SSD or SDD, and what is the field size recommended into specifications. So these tables will quickly show you the KQ factor at different MSR conditions, or the when you deviate from a standard beam, when you move from the FF beam to the triple F beam, and those can be used. So these are basically a function of the beam quality which you are using in the clinic, and they are mentioned with respect to these beam qualities. You have your factors used in the table. You can use those factors into your calculations. Of course, there is also one table which shows you how to calculate the equivalent square field. We call it as an S-CLIN, and which is being demonstrated in my one of the slide coming ahead. So this is basically a measurement condition mentioned in the TRS code, which will be giving you an insight of those methodologies. So these are basically the table which shows you what are the composition of the material in different solid water phantoms. And my earnest request, if you are in a team, as a procurement team for the dosimetry equipment, have a look into it, get a certification from the vendor, and see that they give you the nominal density in a certificate, so that your uncertainty and ambiguity will be minimal in the estimation. Okay, so these are the small volume chambers which are being mentioned into the slides as a function of depth dose, as a function of TPI 2010, and whichever the detector is available in your center, you may start your project for the small field. Apart from these ion chambers, definitely the detectors, the diamond detectors, and the diodes are also very useful. So let us move now what we did in our hospital. One of our two students, one was working on the linear oscillator as a 10 MV flattening filter beam, and one on the tomotherapy. So quickly, we will, another 20 minutes, we should be able to cover up. So reference dosimetry we conducted for 6 chambers, the 3 field sizes, 10, 6, and 4x4. There will be many questions on those, but we were a part of an IEA project where there was a specific agenda, and we followed those agenda. And almost 10 countries were participating into it, and we need to compare the results with other countries as well. So we started with the detectors, then absorbed dose to water, beam quality index was measured. We also did a cross calibration in 10 MV beam. We did measurements in water as well as solid water. We also did in SSD and SAD setup, and then finally we estimated our uncertainty budget as well. So quickly moving, we use the true beam, we use the electrometer, RFA, and 1D water tank as well, and these detectors which are mentioned. So cable and connectors are very important because we have several detectors and electrometers and cable. The combination and the perturbation has to be checked a day before when you are measuring the equipments. So this was our quick approach: select the chamber on the basis of volume, move to the absorbed dose to water, beam quality, move to the cross calibration, and then again select the chamber on the basis of range of lateral charge particle equilibrium, go to the cross line profile, and then output factor. So these two components comes as a part of the relative measurement, and next speaker is going to cover into that. But this was our probably the flow chart and the analysis of the uncertainty budget. So quickly, how to measure your convert into your the beam quality as per this Palmer's equation, very famous equation. So whatever the set clinical field size, and these are the empirical formulas mentioned in the code, and you can convert these to bring it to beam quality to the reference conditions as well. So beam quality in water for these detectors was measured. So this was for 2010 MSR field sizes for this one, and this was for determined for the Palmer's equation. And you can see here for FC65, we did not measure. Reason: the chamber is not suitable to use in the 4x4. So this is basically an outlier. It was not that we did not get time or we don't want to do it. The beam quality in slabs also was checked, and they were compared, and the results were very well acceptable and more or less close. Chamber selection was again verified value with respect to this formula mentioned in TRS 483. I have given you the details as well. Also need to check the FWHM with this formula. And for one slide, we'll show you for particular CC01 chamber, these are the dimensions. This is one example. And then we calculated FWHM and finally come to a value at a depth of 10 centimeter and whether this chamber is available or not under for particular measurement. So the CC01 chamber can be used up to 4 by 4 centimeter without volume averaging effect. This does not mean that I cannot use it below 4 by 4 up to 0.5 by 0.5. However, you need to apply correct correction factors for those detectors as such. So then we had and observed those two water measurements set up, and this is just a quick glance to show how we went ahead. Then formalism by applying the correction factors. Uncertainty was also measured and it is being given. This is basically, these were the conditions and measurement parameters. These are very standard and we maintain those. And this was basically a comparison. If you see here in SAD and SSD, we all measured with the different detectors as well. Then, as the question was coming in the previous talk, that I may have several chambers, the calibration must have been expired. What to do in that? In that case, you definitely go ahead one step and cross-calibrate your detector. So this was also one of the agenda in our IEA project, and we cross-calibrated in terms of the MSR field, and this was given in terms of the cross-calibration. We did it in water phantom and slab phantom. Definitely question will come, but if at all there is a situation that you don't have a water phantom, but you must do, doing something is better than nothing, and get a discuss with the people in your institute, in the city, and in the places where they have the facilities. Share your results with them. So definitely, then from there you will come to the output factors. So they will call as an omega factor or field corrected factor output factors, and they can be defined with the different methods, so-called as the beam daisy chaining method, etc. So we evaluated for different chambers as our project. Very important, the uncertainty budget. I will now explain you about the expression of uncertainties. The literature is available. So type A denoted by the mu A, and the type B denoted by mu B. So this is basically expanded uncertainties, and you need to accumulate both to find out the total uncertainty with that. So we did it for particularly for meter reading, for a polarity, then monitor units, the KTP, definitely. So type B, the monitor units, I can't basically set 200 and all. So we need to do, they come under the type B because they will have a list count of setting. The temperature, pressure, you can't change their scale, which is being used. So these, some of the components comes under the type B uncertainty, which was evaluated in terms of the project of this. And then we estimated the other uncertainties, and particularly for a particular detector with a different voltage as mentioned in the previous speaker. And then ultimately we sum up. So uncertainty in meter reading, the polarity, monitor units, temperature, NDW, the beam quality correction factor, and then finally it came to a factor of coverage factor of 2, confidence limit 95%. And you must understand these uncertainties. Very, very important when you deviate from the nominal standard fields as such. So this is basically in omega factor uncertainty. I would just like to mention about that. Probably next speaker will tell you, when you use a solid water phantom and a detector, the positioning of chamber is very, very crucial. Don't forget to take an either APD image or maybe a CPCT image so that you position your detector very accurately and document it. So then we move to the next beam. So probably in true beam, we could see that there were some challenges. We could see that some detectors were useful for some parameters, and some diodes will be having a positional uncertainty compared to the other chambers as well. So they will be associated uncertainties. Until unless you experiment it, you will not be estimated. So having said that, we did our measurements, and then as a part of this project, IEA sent us the TLDs, we read it, and all the results were within the acceptable tolerance. We moved to the configuring or planning system Eclipse, and we had some associated challenges, but we could succeed it. And then finally, we could publish a paper which previous year, last 2020, for this formalism, and you could go through this paper in detail. If you don't get it, I would be happy to share it with you. Next, probably 10 minutes, I will share the tomotherapy, which we call it as an unconventional LINAC with a triple F beam, so that the spectrum is totally different now. So we had this machine, we had an electrometer, which is an 8-channel from standard imaging and the different chambers. So we then came down to only 2 chambers, reason having that 2 detectors should be used to cross-verify that am I okay with the chamber? Are my readings satisfactory? Are they comparable? So you must have another chamber in a backup to cross-verify your experiments. And an diode, probably an unshielded diode detector, is preferable to measure, because some of the smaller field chambers, which will be difficult, they can be used. So this is the machine which we use, and we have isoscender distance of 85 centimeter. We have 6 MV beam. We have multi-leaf collimators, and this machine cannot be used without multi-leaf collimator, as one of the jaw is basically a multi-leaf collimator. So these are the phantoms which you use. There is a dedicated water tank, and if you want to use it in 2 directions, you need to rotate it when you complete a lateral and a longitudinal profiles. The solid water phantoms provided by the Scanitronics is being also used, and the same formula again with respect to the beam quality was found out, and then the beam quality was estimated from the Palmer's equation, and the standard deviation was very well acceptable for this. So we did those measurements and then found out that out of these detectors, which detector is suitable to go ahead, what it would be the FWHM, and then we move ahead for those factors. So as I mentioned, this was the basically a MSR field used in this one. Equivalent square field was calculated in terms of S clean, which is mentioned, square root of A and B. A and B, don't get confused, follow IEC convention, so you will be self-understood that what is A and B. So you do not get confused and discourage yourself. So again, we did in TSD and TAD, it was difficult, but we need to spend some more time and do accurately, spend extra efforts, how we can do in SSD and SAD setup. Again, we also estimated the uncertainty in omega factor in other meter reading as well, and which was very important to mention into the, so if you see the temperature, pressure, so probably I would just suggest you that any activity, if you do, put it on a paper and you say that what are the contributing factors to that procedure, and automatically you will understand what uncertainties you need to estimate and take into account into your measurements. So automatically you will understand. So if you see the positional uncertainty is very crucial, and with respect to the equivalent field size, what uncertainties in the total components with the different detectors. So we already had extensive study on that, and some of the results we got probably had a lot of observations that the lessons learned. I would just like to share. The one is about the water tank. We need to rotate it. Some of the measurements were definitely not suitable. The measurement for the field size 5 by 40, it becomes an elongated field. So it doesn't fit into the aspect ratio of 0.7 and 1.4 mentioned in the TRS. So these are some of the challenges. And when you go to the smallest field, you assume that your detector will be in the center of the field, but it is not. You may have to shift your detector off axis by 2 to 3 millimeter, and it is very crucial. Even if you miss a millimeter, your detector response is going to underestimate the output factors. Again, we did the TLD irradiations for our measurements, and we had some observation and good results for those. So these basically the beam sizes and reference dosimetry was challenges with respect to these. We measured those output factors, and then this paper we submitted to Journal of Medical Physics, and it is in press and hopefully to see in the soon for the readers to available. These are the references, but there are plenty of references at the literatures available. Just explore and start reading, understand the terminologies, but basically read TRS 398, TRS 483, the IPM 103, and the uncertainty document. These 4 documents will give you a complete picture how to go ahead. And of course, we all are there to help you, to take you into the team of small field dosimetry project. So I would acknowledge again the AFOMP, MP, the organizers, all the dignitaries in the National International Forum, my teachers who would have joined, my students, the faculty, and most importantly, the participant. I would mention that when I was watching Dr. Rajesh Sharma's lecture, in the participants, the number of participants were increasing like a share market. I could see 250, 260, 270, and so on. And I could see now currently there are a number of, they may be in groups. So definitely, as yesterday Dr. Chaubule has mentioned, that around 700 people have registered and they may be attending in a group. It is definitely a hats off to our scientific communities. Hats off to all of you to start this mission as a AFOMP school. And we are privileged to have a part of this. I would just like to mention our new proton therapy facility is now at present under commissioning, and very soon we will be clinical by end of the year or early next year. So we would like to invite you to this proton therapy center for symposiums and visits as such. I would like to thank my 2 students, Vinay and Suryakant. They did an extensive work in a project, and ultimately a project was concluded in a publication which is scientifically peer-reviewed work. And I would thank you so much.
So thank you, Dr. Rajesh Kincar. It was a nice lecture. You have started with the definition of the small photon field, and basically, as we were aware, it was related with the machine-specific reference field, and you have summarized the almost TRS 489 and 483 with its implementability through a IAA project. So I hope this was useful for all the participants, and it carried a number of good information which can be used clinically. So I was going through the chat box and I see there are 2-3 questions. So I will request you to please answer this query. First question is, can we do dosimetry using plan class specific reference method in our clinical scenario?
Yes, the answer is yes. So the plant class reference field dosimetry is one of the important components. We may correlate this to end-to-end test or probably a patient-specific quality assurance. Ultimately, somewhere your planning system will not be accessible to input your beam data, but your plan class reference field would be a different one in a particular plan. So yes, it is possible.
Okay, thank you. So now another question, I think it is related to the same. Is it possible to use PCSR dosimetry? So I think you have already answered. And you have many participants have thank you for this lecture. So I, on behalf of AFOMP, I will say, on behalf of AFOMP, thank you for sparing time and sharing this material with the students, working students, and all of us. It is informative to all of us. So thank you very much once again.
Thank you.
Okay. So now our next speaker is Dr. Sudesh Deshpande. He is also our colleague from CD Hinduja Hospital in Mumbai. He is the chief consultant medical physicist in the radiotherapy department of PD Hinduja Hospital. And more closely, we are very closely associated with each other from not now, from I hope it is more than 25 years. He has done a lot of work in the field of radiotherapy and especially radiation dosimetry, treatment planning, and he is involved in teaching and training as well. So rather than wasting time in giving other details of Dr. Sudesh Deshpande, I will like to listen to him. And before that, I want to tell you that he interacts with many of the experts world over, and he was one probably that when a small field was an area where people were talking, brought this topic to us that we should have some program in India, I think about 10 years back. So Dr. Sudesh Deshpande, it will be our pleasure to listen to you for the relative dosimetry of conventional and a small static photon beams. Thank you.
Good afternoon, everybody. Can you listen me?
Clearly.
Yeah, yes.
Clear, no problem.
And can you see my slides also?
Yeah, exactly. No problem. Fine.
Yes.
Good afternoon. I sincerely thanks Dr. Chaudhary and Dr. H. Sharma for inviting me and to give opportunity to present about the relative dosimetry and relative dosimetry of conventional and small static photon beams. Let me clear first things for the participant. After seeing the Rajesh Kincar's lecture, he has gone in depth about the theoretical knowledge about the small field dosimetry. After seeing the Dr. L.G. Sharma lecture, you had seen about the how to do the reference dosimetry. I'm not going to tell you any formulas. I'm going to tell what are the practical aspects when we do a relative dosimetry for a conventional and the small static photon beam. So my topic is mainly oriented only what are the practical things, how we can do the relative dosimetry that includes the output measurement, PDD measurement, and the beam profile measurements. So more I will talk in about what are the practical issues. Again, my topic, since it has to cover the both conventional field sizes and the small photon beam sizes, I will be more focusing on the small photon beams, because if we can do the small photon beams dosimetry, if we can achieve the accuracy what we require for a small photon beam, definitely we can do a better job in our conventional beams. So a little bit about the outline of the talk. I will talk about the importance of the small field dosimetry, small field dosimetry definition, that already Rajesh had covered and he had done the good job for me. So I will try to skip all these things. Then I will spend some more time on the selection of the detectors, because when we do a relative dosimetry, the selection of detector is very important. So what are the errors, what has been happened in the past, are that mainly because of the selection of the detectors. So selection of the detectors is very important. So I will spend some time on the selection of the detector, what are the detectors available. Then I will talk something about the TRS 483 formalism. I will not talk anything about the TRS 483 formalism, about the reference dosimetry. I will only talk about the relative dosimetry, and I assure you, I will show you, or I will talk only about the one formula. I will not speak anything other than the single formula. Then I will talk about the mechanical accuracy of the machine, why it is important, and I will talk about the setup accuracy. When we do a setup accuracy, what are the challenges, what are the things we should look for when we do a relative dosimetry. We always talk about whenever we do a treatment, we always talk about the high quality treatment. So the definition of the high quality of treatment is defined in the medical physics in 2007. They had defined what is the high quality treatment. The high quality means minimizing the process variation and moving to the average closer to the optimum value. So for high quality, we had to have a very small systematic errors to hit our target properly. So, and the important factor comes in that high quality is the commissioning or the dosimetric characters of your machines. So if you have introduced any error when you do a commissioning, that error will be there throughout the treatment for the many patients. So the importance of the dosimetry is very, very important for the high quality of treatment. So we might have seen the lot of changes in the technology and how this technology has changed. Till 2000, we were talking about the 4x4 fill sizes. That time we were dealing with the 3D CRT and the IMRT. The IMRT had just begun in the year 2000 or 1998 or 1999. But that time we were talking about the 4x4 fill sizes, and doing a dosimetry for 4x4 fill size was not that challenging. Then we moved to 2006. We were talking about the SRS and SRT, SRS and VMAT, where we were configuring the machine up to 3x3. Then comes the SRS and SBRT. We were configuring the machine up to 2x2. Then we have cones up to 0.5 by 0.5 in 2012 onward. If you see the literature, the people are talking about the 0.5 centimeter into 0.5 centimeter relative and absolute dosimetry. This is with the MLCs. Now we have the specialized machines like the cones and helmet, gamma knife, where we have a dosimeter, where we have cones of 4 millimeter to 16 millimeter, brain lab 4 millimeter to 15 millimeter. Then we have a cyber knife where we have the cone from 4 millimeter to 75 millimeter. For conventional fills, that is greater than 4x4 fill size, we have AFM task group 106, which clearly explains how to do the measurement, for output factor, what are the precautions we have to take when we do a measurement, what are the challenges, what are the conditions we should look for the measurement of the output factor, profiles, and the PDD for the fill size greater than 4x4. But when it comes to the smaller fill size, that is the fill size less than 4x4, the 4x4 fill size is very, very different than the 0.5 by 0.5 fill size. As earlier speaker Rajesh has explained is very well what are the problems associated with the smaller fill. So that is the challenging things. And that is challenging not only for a reference dosimetry, it is also challenging for the relative dosimetry. So what are the things we should look for when we do a relative dosimetry for a small field? That has been explained very well in the task group 155, which is recently published 10 days back. It is available on the online, it is in the press. That is APM task groups 155 and TRS 483. Both documents, TG 155 and TRS 483, explains us what are the things we should look for when we do a relative dosimetry for a small field, and APM task group 106, which tells us what are the things we should look when we do a reference or absolute or commissioning of the equipment for the fill size more than 4x4 fill sizes. Now, what we have also noticed in our country or in many parts of the world, there is a sharp increase in the number of centers practicing the SRS and SBRT. So as the number of centers are increasing who are practicing the SRS and SBRT, the small field plays a very dominant role, and knowledge of the small field is very, very important. Again, this is something overlapping of the slide, but I will not explain this entirely, but just for a continuation, I will go through the slide for the definition of the small field. That for the selector energy and the medium, the field size is not large enough to ensure the lateral charge particle equilibrium. The second point, the entire source is not in the detector's eye view, that is the source oscillation is happening, and detector is not small enough and perturb the fluence significantly, that is the detector issue. Whenever there are three condition happens, we say that we are in the small field. The Rajesh has clearly explained this. I will just skip this. Okay. Now these are some specialized equipments. This is the gamma knife, what we have in our department, that is the perfection. This is then we have the cone-based system. This is the cyber knife. This is the inbuilt micro MLC, or that is the HD MLC, and there are the additional MLC, that is attached MLC, like what we used to have in the brain lab MLC. So these are the specialized equipments. And whenever we do a commissioning of this equipment, there are two dosimetry, or there are two factors that are very, very important, is a reference dosimetry and the relative dosimetry. So this relative dosimetry plays very important role when we do a commissioning of this any equipment like gamma knife or tomotherapy or even our conventional linear accelerator. When we do a relative dosimetry, what is the relative dosimetry? A full dosimetric characterization of clinical use required whenever we want to use the machine for the clinical use, the calibration of the beam under reference condition, and we require the field output factor. They are necessary for the calculation of the monitor units or the treatment times in the gamma knife. We require a central axis percentage dose, that is we call it as a PDD. We require a TMR or TPR and the lateral beam profiles. Nowadays, most of the planning system doesn't require the TMR and TPR, they only require the PDDs. So whenever we do a commissioning of the machine, we require the field output factors, we require the PDDs, and we require the lateral beam profiles. So whenever we do a relative dosimetry, the important factor is the selection of the detector, which detector we should use. So we first, an important thing, we should know the characteristic on which the property of the chamber can vary. The first, the density of the sensitive volume, how much variation in the density with respect to the water of the sensitive volume, atomic properties of the sensitive volume, that is what is the electrode, that is which type of central electrode is there, whether it is steel electrode or it is the aluminum electrode. Depending upon the property of that electrode, it will have the different interaction with the radiation, and if it is high Z material, it may over response. If it is not, so the properties of the sensitive value, the atomic properties are also important. So we should know what are the atomic properties of the sensitive volume. Then the presence of the extracameral component for the manufacturing purpose or for the stability of the detectors. There are some high Z materials displays. How this high Z material impact our dosimetry, that is also important. And the last, but which is very important, is the volume averaging. What is the volume of that? So depending on these four characters of the, these are the four important characters we should understand before using these chambers for a relative dosimetry. Again, the selection of the detectors. See, this is the quite famous curve we had seen in the many presentation. If you just put on the Google small field dosimetry, we will see this Indrajit Das paper of the Journal of Radiosurgery, what he published in 2000. What he found out, if you measure the output factor with a different detector, he had observed the maximum variation of the 14%. And the first thing comes in our mind is that, oh, he has not used the chamber properly. He has used the larger chamber. But which detector we should use? Can we say that only micro chamber will solve all the problems? No, it's not only the volume of the chamber is important. It is the energy dependence and the perturbation effect. For example, this is the paper published in the British Journal of Radiology. If you see the field size output factor comparison, for 2x2 to 10x10 field size, it has used all the different chambers, that is ionization chamber, plastic scintillation, again ionization chamber. It has come, and the edge detector. If you see from 2x2 to 10x10 field size, the most of the chambers do very well. But just look what happens for the field size less than 1x1 for the edge detector. See, it overestimates nearly 10 to 12%. It is also a micro chamber. It is also, its dimensions is very, very small. So it's not the only volume averaging that causes the error when we do a relative measurement. So the distribution will be explained due to the presence of the non-water equivalent material in the active or non-active part of the edge detector. That is the very high, that is the high Z material is present, and that because of that presence of the high Z material, it is over responding. So the selection of the detector is very important. Okay. Now, we had seen that because of the presence of the some component or because of the presence of the larger volume, we had our output factors are not matching to the actual or the calculated or Monte Carlo calculated output factor. So to address this, the TRS 483, this code of practice deals with the reference dosimetry as well as the relative dosimetry. So Rajesh has clearly explained about the reference dosimetry, and this code also explain about the relative dosimetry. What are the factors we should consider when we do a output factor correction? This is the TRS 483 formalism. We know we have the reference field size 10 by 10 for the conventional beam. Then we had introduced the concept of the machine specific reference size, that is FMSR. For example, gamma knife, the FMSR is a 1.6 centimeter. But we most of the time when we do a clinical treatment, we are not going to use this machine specific reference field size. We require a clinical field size, that is F clinical. Now we know the calibration, we know the factor which convert the reference field size from the 10 by 10 to the machine specific reference size. But there is another factor that converts the machine specific reference field size to the clinical field size, that is we are going to actually use for the patient or during the treatment. So this correction factor is also important, and that is well explained in the TRS 483. I will come to that factor. Now, I will go a little bit in depth about the choice of the detectors. If you go to literature, there are many detectors available in the literature, and there are many detectors available in the most of the department. Now, if you define the detectors in a particular group, we have a first group that is from 0.3 to 0.6 centimeter. That is the formal chamber, and till the dimension of 0.3 cc. Chambers are not suitable for relative dosimetry for a small field size. 0.3 detector is good till 4x4 field size, even good for a PDD. But for the small field size, the size is too large, and they underestimate the absorbed dose to the water. These chambers are not.
सेव्ह करायचं.
Okay, these chambers are to be avoided for a profile measurement for a small field, as correction volume of averaging effect are unacceptably high. So up to 0.3 cc, we can do a measurement, or we can do a measurement with the accuracy till field size 4x4. Now we have another group of chamber, what we call as a mini chambers or the pinpoint chamber. They are generally of the 0.1 cc to the 0.3 cc. They are suitable for measurement up to field size 2x2 field size, 2x2 cm square. They have good energy response, uniform directional response, and they are independent of the dose rate. So they are good, these mini chambers and the pinpoint chambers, to do a dosimetry till 2x2 field size. Then we have another group of chambers that we call as the micro chambers. Their dimension is from 0.02 cc to 0.01 cc. Their volume averaging effect is very, very less, but they have a limitation. Since their volume is very small, they have the reduced sensitivity. Their response is less. And they are also associated with the signal leakage. Since their sensitivity is less, the signal leakage needs to be corrected. Okay. Now we have the problem with these small chambers with the sensitivity. To overcome this problem, we have the liquid ionization chamber. This liquid ionization chamber, the difference is that instead of the air, what we had seen in the earlier micro chamber, the dielectric liquid is used instead of the air. And because of the high density of the liquid, the sensitivity is significantly larger than that of the air filled. So whatever the limitation was there, we have overcome that limitation by introducing the liquid ion chamber. But this liquid ion chamber required the bias voltage more than 800 volt. Their response is a dose rate dependence, and there is a substantial recombination effects. These are about the chambers. Now we have another solid state detectors, that is the silicon diodes. Silicon diodes are have generally small volumes, and there is a small volume averaging effect, but they are angular dependence because of the construction, internal construction. Diode are also known for over response in the low energy photons, so we need to take care of that. And shielded diodes are the energy compensated. We can use the shielded diodes to absorb the low energy, but they contain the high density material. The presence of the tungsten increases the fluence of the secondary electron in the silicon win and the higher mass energy absorption coefficient of the tungsten, so they over response. So these are the things we should look for when we use the shielded and the non-shielded diodes. Then there is a called as a diamond detectors. Diamond detectors are the very high sensitive. They response independent of the energy, but they are also dose rate dependence. Then now the chambers that is getting more and more popular, that is the plastic or the organic scintillators. These detectors works on the principle of the production of the light when they are exposed to the radiation. The plastic scintillation dosimeter can be made very small, up to 1 mm cube, and they have the good sensitivity for the clinical dosimetry. Scintillator response are generally linear in the absorbed dose to the water length for the therapeutic interest. Perturbation correction factor for the plastic for the small fill are close to 1. So they are becoming, because of this, all four favorable reasons, they are becoming more and more popular. The last but not the least is our films. The films are always called as the gold standard when we do a profile measurement, and because of the very high spatial resolution, we had a problem with the radiographic film. Now we are not, most of the centers are moving from the radiographic film to the radiochromic film. So whatever the problems associated with the radiographic of the development, the process, and the storage of the film, they are all been overcome in the radiochromic film. So the radiographic films are becoming very popular nowadays. This is all about the detectors. I will not go about the definition of the field size because Rajesh has explained this very well. So he has explained what is the geometrical field size and what is the irradiated field size. But there are three conditions what we have to look when it comes to the field size. One, for a large field size, for a field size equal to the charged particle lateral equilibrium, and very small field size. When it comes to the large field size, when we take the full width half maximum, the actual field size and the full width half maximum becomes same. But when we at the B condition, that is when we select the field size of the charged particle equilibrium, then the error is small. But when we have the field size smaller than the large lateral charge particle equilibrium, then the full width half maximum, if you draw the full width half maximum, it will be the more than the actual collimator size. So we have to always mention the full width half maximum when we deals with the smaller field size. And TRS 483 advises that for small field dosimetry, field size is reported as the full width half maximum of the field, because all the correction factors are explained in the full width half maximum. Okay. Now we have to understand the alignment accuracy. Whenever we do a relative dosimetry, the machine alignment, that is machine quality assurance, is the perfect. Nowadays, all the machines are coming are with the mechanical accuracy less than 1 millimeter. For example, now what we have the linear accelerator, whether it is from Varian or it is from the Electa, the isocenter accuracy, they are mentioning, the vendors are mentioning from 0.1 to 1 millimeter dia. The tomotherapy accuracy is of 0.5 to in degree or 0.5 millimeter accuracy we can achieve. In our gamma knife, it is 0.5 millimeter, or cyber knife, it is 0.4 mm. So when we have such a accuracy, this accuracy is very important when we do a measurement. For example, now we have 6 millimeter, 6 by 6 millimeter field size. And when we are doing the profile measurement, look at if you have 1 degree offset, we can see the clearly variation in our profile. The profiles are shifted in one direction. And if you do a measurement, with such a condition, and if you feed this data to the computer planning system, you are introducing the error. And this error will be there for all the patient. So whenever we do a relative dosimetry, the mechanical accuracy of the machine is very, very important. So whenever we do any measurement, please ensure that your machine is perfect. Again, when we do a measurement of the PDD, how the mechanical accuracy is important. This is the beam where we have not applied any correction, or it is actual measurement. When we have 1 degree of variation, see the variation in the PDD. What we observe that there is not much change in the initial depth, but at the lower depth, the contribution of the error is more, or it is dominant. Even for the 0.5 degree, we can see there is a variation. If we have a shift of 2 millimeter, definitely we are underestimated and see the PDD. So again, the mechanical accuracy plays very important role when we do a measurement, relative measurement, whether it is a PDD or whether it is a lateral beam profiles. Okay. Now, detector before first use, or in other words, we can say what is the QA, or what the QA we should do when we are using the detector for the first time. For accurate measurement, it is better, or it is a good practice whenever we get any new detector, do a theta radiograph, theta X-ray in a AP and lateral direction, that is theta orthogonal radiograph. How this will help? This will help to identify any potential problem with the detector, assess the construction of the detector, and the symmetry of the detectors. Whether there is any potential problem, whether you find there is a asymmetry of the detector, then you can identify before putting it in your RFA, or before putting for a measurement. This will also help us to determine the location of the sensitive volume of the detector, which may differ from the external mark or the information provided by the manufacturer to the extent significantly. So sometimes there can be error. We generally align our detectors according to the manufacturer mark which is provided on the detector. But why should we believe on the detector manufacturer values or manufacturer mark? Better to take a radiograph before use and just verify what is the location of the sensitive volume and whether it is matching with the whatever the provided mark provided by the vendor. Just verify it. If you are satisfied, then use it. If you feel that require some changes, you can definitely do. Where necessary, the angular response of the diameter of the detector should be measured to confirm any asymmetricity. We know that the diodes are the angular dependent, but for a good practice, whenever we get any chamber, before putting that chamber in for measurement, actual measurement, check the angular response of the detector. There may be some construction issue, or you may find some good results. Okay. Measurement setup accuracy. That is very important when we do a measurement for a relative. Now, earlier in my slides, I spoke about the mechanical accuracy of the machine. Now, we will talk something about the measurement setup accuracy. When we set the phantom, when we set the detector for a measurement, what are the things we are looking? For relative dosimetry, ensure the placement of the detector in the center of the radiation field. Generally, in the most of the cases nowadays, we do a alignment with the lasers. It may possible that your laser may not be aligned with your central beam axis. Now, how to do this alignment of the detector? The best way is to use the RFA for a detector alignment, because it is very difficult to align a detector within or less than 1 millimeter accuracy. So it's better to use the RFA to align the detector, whether you are measuring the small field output factor or you are doing the profile also, or even for any related dosimetry, use RFA for aligning your detector. Scan the lateral profile in the XY direction and check the alignment in a different depth. So if you do a profile in the XY direction at different depth, you will clearly see after visualizing your profiles at different depth, it will clearly tell us that how much you are shifted from the exact beam center. Now, in TG 155, it is recommended that the detector must be correctly mounted and precisely aligned within plus minus 0.1 mm and oriented to the central axis of the beam at all depths. So now it is expected to have an alignment within 0.1 millimeter. It is very difficult to align this with the naked eye. So whenever we do alignment, use the RFA, scan it in the X and Y direction at the different depth, look at the profile, or many RFA system will give us the centership, apply the centership, scan it at different depth. Whenever you do again measurement after scan, then by applying the centership, you should not see any center shift when we do measurement. So it is very important to align the detector properly. Okay. Now, output factor measurement. In conventional field, how we used to do the output factor measurement? It is very simple thing. We used to put a chamber at 10 centimeter depth, measure the reading at 10 by 10 field size, and measure the and then measure the reading, take the reading at different field size from 4 by 4 to 6 by 6 to 40 by 4. And we used to find the output factor by taking the ratio for the field size to the reference field size, that is the 10 by 10. So this was a very simple thing. But now what we observe in the small field, the field output factor that is absorbed dose for a small field, F clinical, that is F clinical is the field size that we are going to use for the clinical practice, with reference to absorbed dose in the MSR field, that is now we are defining this as a machine specific reference field size, is derived from the ratio of the detector reading. So it's the alpha, that is omega factor, that the output factor is equal to dose at the clinical field size divided by the dose at FMSR. But it has been observed that this value doesn't give the correct value for the small field size. So we had introduced one factor, that is K factor, that is we called as a small field output correction factor. When we apply this output correction factor, we will get the exact or correct value. Now, this factor accounts why we want to apply this factor. This factor accounts any influence from the volume averaging effect, that is the size of the detector, as well as the perturbation effects. As we had seen in case of the edge detector, there was some perturbation effect, or this factor takes into account the correction factor. Now, how to calculate this factor? You can do directly measurement value or experimental generic value, or nowadays, or we have a ready-made Monte Carlo calculated generic value available in the TRS 483. So this new concept of the small field output for the small field output correction factor. We need to apply this whenever we do a output factor measurement for the small field. We were not doing this for a conventional field. Anything field size more than 4 by 4, we used to measure a directly ratio of 4 by 4 field size to the reference field size that was of a 10 by 10 field size. But for the small field size, it is recommended whenever we calculate the output factor for a small field, we have to apply the output correction factor to the ratio of our clinical field size to the ratio of the ratio of the clinical field size to the ratio of machine specific reference field size. What is this output correction factor? If you go to TRS 483, they had defined for different chambers for unshielded diodes. For small field, you can see it is ranging from 0.94 for field size 8 by 8. We can see that at 8 by 8 is nearly 1. The same for the IBA SFD. Again, then this is for the IBA CC01 chamber, and this is for the Estradin IC chamber A16 chamber. So these are the output correction factor which needs to be applied for the small field related dosimetry. Now, one thing what we had seen that these SFD detector or these diodes, the factor is less than 1, and for the ion chamber, the factor is more than 1. So whenever we had been told that the output factor should be measured with the 2 different chambers. So now the question comes, which are the 2 different chambers? So it is advisable to select a such a chamber, that one chamber which has a output correction factor less than 1, and select another chamber which has the output correction factor more than 1 for a small field size of less than 3 by 3. So instead of using the output factor with the 2 different chamber of the, for example, it will not make any sense if you measure the output factor with the 2 different chamber from the one PTW diode and the SFD diode from the IBA, because it will not give any difference in the measurement. But it is always will be a good practice if you have 2 chambers where the output correction factor for the one chamber it is less than 1 and the other chamber which is more than 1. So choice of the detector for 2 different, when we say that we should measure the output factor with the 2 different chamber, we should keep in the mind what is the output correction factor when we select the detectors. Now, again, as I told you, I will talk about the practical things. Whenever we do a PDD measurement or the profile measurement, what are the challenges when we face when we put a RFA? The first and the important is a choice of appropriate detector. As I told you, there are different detectors available, and depending upon what field size you are using, if you are using the conventional field size more than 4 by 4, the 0.3 cc will also do your work. But when it comes to the smaller field size, what type of chamber we had to use, that is the important question. Then alignment and the orientation of the detector with respect to central axis. I will talk about this in little bit detail in the next slide. Alignment of the detector axis to the beam central axis at all the depth, that is very important. So again, for alignment of the detector axis to the beam central axis, stand in X and Y direction, take the beam profile at various depths and align your detector exactly to the beam central axis. Position accuracy in the defining the field. That is, again, it is related to the mechanical accuracy of the machine. That is very important. Now, placement of the reference detector within the small field. When we were measuring the conventional field size 4 by 4, the field size is sufficient to accommodate the 2 chambers. One is the central chamber, or that is the chamber, and the another one is the reference chamber. But when our field size get reduced and reduced, Then the question comes where to put a reference chamber. Now there are new RFA or new software which are coming where they are putting the reference chamber at the mount of the gantry, or some people are even putting the reference detector inside the phantom. And because they have with the new software availability where we can change the gain of the reference detector and the field detector so that we can get the same signal. So placing of the detector in the field is not now the problem has been solved, because with the new RFA, people are not putting the detector in the small field. They are putting on the gantry mount, or even they are putting at the bottom of the RFA. And now you may question how it is measuring, because we require only the ratio of the field detector and the reference detector. Now if your detector is not in the field but it is measuring some signal, now we can apply a different amplification factor and we can measure the things. Otherwise, if you have the old RFA where these new type of detectors are not available, uh, we can just do a measurement with the only field detector. But there, what we had to look that our chamber is moving very slowly, and we are taking the measurement, minimum 5 measurement at every position. Then monitoring the machine output fluctuation, because that is very important when we are not using any reference detector. Then the last important point, which doesn't much make difference, that is the physical size of detector, since it may not correspond to the size and the position of the sensitive volume. Yes, what I told you earlier, that the sensitive volume, the mark of the sensitive volume is very important. Okay. Now, orientation of the detector with the central axis. How my detector should move when we do a beam profile. This is the first is on the left hand side. This is for the ion chamber. The better is that if you can mount the ion chamber in a vertical position, then we can scan in the both direction. We will not have any problem. Now the second condition, generally we use our ion chamber in a in a horizontal direction. In this feeder in the left most feeder, in the central feeder, we can see that this position is good to scan in a y direction, that is the perpendicular to the paper. That is the possible orientation of the ionization chamber for so this is good when we are measuring the perpendicular to the paper. Now the paper plane axis. This is not good when you are measuring parallel this among the two direction what it has been shown, because when we are measuring, it will have the gradient when the chamber will experience the gradient when it comes near to the boundary of the beam. So it is not advisable to, when we are measuring in the x direction, for example, this is the x direction, this should not be the orientation of my chamber. When it comes to the diodes, when we do a scanning, the diodes should be always placed vertically up. It is recommended that diode should be when we do a measurement, the diode should be vertically up. It is not advisable to mount the diodes in a horizontal position. It has to be always in a vertical position. These things we have to keep in the mind when we do a orientation of detector for the RFA measurement. Okay. When we do a lateral beam profile, again we can see here that with the different chamber we have a different penumbras, and this selection of the detector becomes very important when our field size reduces for the less than 4x4 field size. For a conventional field size, again, I'm not telling that we should do like this, but for the conventional field size up to 4x4, the small error in the penumbra will not much affect your commissioning for the larger field size. because when we use the IMRT or VMAT, we have the smaller field size, less than 4 by 4. And there, the importance of the penumbra is very important, because it is the factor, because we will have the many small fields in the IMRT or VMAT, and the penumbra of the each field is very important. And so for the perfect commissioning of the machine, the penumbra is important. And the penumbra is basically depend upon the size of the detector, or that is what we call the volume averaging. So the choice of the detector is very important. Generally, the liquid ion chamber, ion unshielded diodes, micro diamond, organic scintillation, which have a very small sensitive volume, are suitable for the profile measurement. Again, what I told, the radiochromic film is a gold standard. Radiochromic is very suitable for lateral profile measurement, but needs adequate readout and the calibration procedure. Otherwise, the spatial resolution is the best in case of the radiochromic films. Okay, percentage depth dose. Again, the percentage depth dose. Whenever we measure the field size more than 4 by 4, whatever the ionization we had measured, it can be directly converted to the dose. That is not an issue when we have the field size more than 4 by 4. But for the smaller field size, we have the problem. To directly measure the PDD for small field size, the most suitable detector is the microionization chamber, or even the parallel plate chamber, the small parallel plate chamber. It is always recommended to use the parallel plate chamber to measure the PDDs, because in the shallow depth, to get a better curve or to get a better result, it is always advisable to use the parallel plate chambers. The PDD has traditionally been calculated as the ratio of the ionization reading, and the method generally is value larger than 3 by 3 field size. What I told you that for the photon beam, we can directly convert the ionization to the dose for the field size greater than 3 by 3 field. The ratio of reading determine the PDD for the small field might not be valid if the perturbation direction is indeed vary with the depth and the field size, and require accounting for the variation in the measurement. Since for the if the perturbation is quite dominant and it is large in the lower depth, then whatever the PDD we are measuring, that will not be true, or it will have some uncertainty for the small fields. So in general, the detectors that have the smallest what we call as output correction factor, that is should be preferred to avoid to need any to correct any PDDs. Otherwise, it will become a very difficult job to convert the ionization to the depth for the smaller field. Then it will we needed some software manually we cannot do. So it is better to have measure the PDD the detectors where the perturbation correction factor is nearly 1. Okay. Now I have only 2-3 slides more. The sources of uncertainty. So whenever we do a measurement related to dosimetry measurement, what are the uncertainties? Where we should take the precaution? The misalignment of the detector axis with respect to the beam central axis. That can cause the major error. So alignment of the detector and the orientation of the detector is very important. That can cause the uncertainty in your measurement. So you have to do a lot of attention for the alignment of the detector. Then deviation of the vertical motion of the scan arm from the central axis. Oh, means in other words, we have to do a QA of our RFA, our deviation of our scan arm from the central axis, whether this is moving correctly in the central axis, whether it is not getting deviated from the central axis. That also can causes the uncertainty. Inaccuracy in the collimator jaw setting. Yes, your jaw setting is not properly calibrated. That also can cause the uncertainty. Spectral change in the field size result in the incorrect mass top-in power ratio, especially for the linear accelerator operating without the flattening filter. This is some issues with the FFF beam. Incorrect or unknown correction factor to convert the detector to signal dose. That also can cause the problem if you are using the chambers which do not have the proper correction factors. that can cause the uncertainty, or incorrect SSD or measurement depth. If your machine is not properly calibrated, if SSD incorrect, you have used the incorrect SSD, or your measurement depth is not proper, that also can cause the uncertainty. These are the sources of the uncertainty when we do a relative dosimetry or even we do absolute dosimetry. So as a physicist, whenever you start doing a relative dosimetry or absolute dosimetry, we must pay attention to all these points: the detector alignment of the detector axis, deviation of the vertical motions of the scan, inaccuracy of the collimator jaws. Because when we do a accuracy, when we do a measurement for a 2x2 field size or 1x1 field size, the accuracy is, if the chamber, if the calibration of the jaw is not properly, it is variation of 1 mm, so it causes the 10% error, because for 1 mm 1 centimeter field size, 1 mm error is around 10%. So accuracy of the collimator calibration is also important. SSD calibration, measurement depth, these all play in your uncertainties. What, okay, now what is the, so as I mentioned, is the sources of the uncertainty. Now this is the curve, the fractional of uncertainty measured for the at the 10 centimeter depth for the field size of 5x5 in the y direction for the 6 mm beam of the Electra machine. So what are the uncertainties? The depth of the detector, position of the detector, alignment, misalignment, statistics, the fluctuation of the machine output, the detector, the sensitivity of the detector. And if you see the total uncertainty, the maximum, the main contribution in the uncertainty is because of the position of the detector. So position of the detector is very important. That causes the main uncertainty. That is the main source of the error. When your detector is not properly positioned, it can causes the error. So all these are then, these are all the small factors that also contribute to your uncertainty, but the dominant factor is the position of your chamber. Okay, at the end of the day, why we are doing all this thing? We are doing all this in measurement to commission our RFA, commission our TPS. So whenever you enter when you do all the measurement, taking all the precaution, you had used the proper chamber, you had used the proper correction factor, you had done the dosimetry up to 1x2 field size, we had done taken the correction, we had properly aligned the detector. But at the end of the day, what is the important? When you commission your RFA, when you commission your TPS, and when we do a quality assurance test for the field sizes, if you're when we do a measurement and when we do a QA of your TPS, your field size, if you calculate your field size from the TPS for a particular vendor, this is for the variant 6 millinet, and this is the data. After doing all this in taking a lot of effort for doing the relative and absolute dosimetry of the machines, our data should be matched, our QA should be of the TPS should match to the published value. So at the end of the day, whatever the precaution you take, it should match, your TPS QA should pass up to field size, I will say up to 1x1 or even the smallest field size you use. But as of now, we have data, published data till 2x2 field size. There may be some data which can be used, but as of now, which is the published data from the RPC for the different accelerator, for the different machines, we have this data. So just do a commissioning of your machine, do a commissioning of your Eclipse, and compare your results with the published data. If your data is matching within your acceptable limit, you have done a wonderful job. Otherwise, whatever the efforts you take, it is not of any use. Okay. Conclusion. Select the small volume detector with the minimal energy, dose and dose rate dependence. The selection of the detector is very important. A detector with known output correction factor, that is preferably close to 1, should be selected, so that whenever we do a PDD measurement, we don't require to apply any correction factor for the small field size at the lower depth. The proper measurement method should be used. Use the proper correction factor, whatever the mention in the guideline. For example, TRS 483 and the TG 155, they are the good reference book whatever the method they had explained during their during their protocol, follow that method, follow the book, so you will not make errors. The resolution of the scanning measurement should be smallest possible to limit to the device. So whatever the smallest possible scanning measurement option is available, that is the step size should be used when you do a profile measurement for a small field size. It doesn't make much difference for the larger field size, that is for the conventional field size. But when we have a field size of 1 millimeter and your step size of 0.25 millimeter or 2.5 millimeter, that will not give a good profile. So whatever the least possible step size available in your RFA or in your scanning instrument, use that fill options. Measurement with the minimum 2 detectors. Yes, because I explain you should have do a measurement with minimum 2 detectors. Again, the selection of the 2 detectors should be such that the output correction factor, or otherwise it should not be from the same class, that is both should not be ionization chamber, both should not be ionization chamber, or both should not be a diode, both should not be diode. So that precaution we had to take. And always compare your results with the published data. That will help you to get a confidence about your data, whatever the measurement you have done, and this will help to the patient that your results are well in acceptable limit. Thank you. Okay.
So thank you, Dr. Sudesh Deshpande. It was pleasure as usual. You have discussed a lot of things, and majorly practical aspects, measurement of beam profile, output factors, and all the parameters required for using the radiotherapy equipment in the clinic. And I hope this lecture was useful for all the participants. So I have seen a few questions from the participants in the chat box. I will just read and I request you to please answer their queries. So you have answered many things, but still some small queries are here. So first question is, what is the recommended percentage of agreement between TPS and measurement accepted?
So accepted criteria, if you go to the measurement, there are some noise. If you go to TG53 or TRS 430, they have defined the TPS keyway. There they had said that the accepted criteria is about the 3%. So if your results are within the 3%, what is the documented in APM task group 53 and the TRS 430, so it should be within the 3%, whatever the output, the TPS result and your measure results.
Now, there is one more question from Dr. VP Pandey. TRS 483 suggests one can obtain data of output factors in a small field by aligning detector parallel to the field. What is your opinion about aligning parallel instead of perpendicular to central axis? What practical challenges we will get in parallel alignment? I hope you have answered this question, but you can repeat here.
Yeah, again, what I told you, the advantage of putting in a, if you have the ionization chamber, if you put it vertically, that is perpendicularly to the axis, we will not have any issue when we do a measurement in the X and Y direction. But when we put it horizontally, then when we scan in the what in the conventional linear on the in X direction, it will have the dose gradient when it reaches to the field junction or the field boundaries. So that may cause the error. So it is always advisable to do a measurement in a vertical direction if you can do it.
Okay. So thank you. Now there is a small suggestion for the organizers of the program. Some of them wanted a webinar on radiobiology. So I will pass on this question to Chogle sir, and I hope we have finished from the speaker's point of view. So I take this opportunity once again to thank the other two colleagues who joined with me for conducting this medical physics school, AFOMP school. And it was the inaugural school, so we are very happy that we have tried, and I hope it has worked for all, and people will definitely get some useful information from these facilitations. And the AFOMP should continue this program. There was a comment from many participants. So now over to Dr. Chaule Sahab. So thank you very much for the opportunity.
Thank you, Professor Dr. S.D. Sharma, for organizing this first AFOMP school webinar very excellently. Your talk, Dr. Rajesh Kincar, and followed by Dr. Sudesh Deshpande. It was very, very excellent overview and in-depth about the reference dosimetry in various aspects has been covered. Very nicely you have taken care. And I think the number of participants started with around 270. Okay, but it's a long one. Now we have around 170 or 80. But it shows 270 participants, about 700 were actually plus were registrants. It shows a very good response and interest in the participants. So we have organized the AFOMP school webinar for July and August. And we would like to get the feedback from the participant so as to plan remaining 4 webinars, school webinars of this year, that is from the September to December. So participants, very thankful to you, AFOMP, for your participation. So next webinar, AFOMP school webinar, will be on 22nd July 2021, and this will be medical physics and advanced cancer services, physics in external beam radiotherapy, and this will be Thomas Cron and his group. They will be giving this webinar. Then we have another webinar already we have planned, that is the 3rd webinar, AFOMP school webinar, and that will be on 21st August 2021. And this will be on precision radiotherapy from biological, physical, and technical aspects. And this will be delivered by 4 speakers from Iran, led by Professor Hossein Mozdarani, and all these topics you can see. Everything is available on the AFOMP website. Then we have the AFOMP webinar, and the 14th webinar will be on 8th of July, that is a Thursday, during 7 to 8 a.m. GMT. And the topic is the IAEA TCS 71, which has come out in February 2021, which gives guidelines for certification of clinically qualified medical physicists. And this will be delivered by Georgia Loretti of IAEA, and I will be moderating. So please try to attend the webinar, which is going to come on 8th July, and then AFOMP school webinar of 22nd July, and the August 21st, which will be the AFOMP school webinar timing is 7:30 a.m. to 9 or 9:30 a.m. GMT, depends upon the length, but it will start at 6:30 a.m. GMT. Though our Zoom link will start at 6 a.m. GMT, actually the webinar will start at 6:30 a.m. GMT. So all this information is available on the AFOMP website. So once again, thanking Dr. S.D. Sharma, Dr. Rajesh Kincar, and Dr. Sudesh Deshpande for taking out the time out of their busy schedule and delivering the talk on a very, very important topic in depth. And the sum of they have written that is a refreshing for some senior people, for the junior in this thing. This topic has helped a lot. All the delegates, thank you very much. I take the opportunity to thank the AFOMP ExCom, and especially the chair of the Education and Training Committee, Professor Jin Xians, and the chair of the PRC, Professor Chai, for taking out time and trying to arrange all these things, which takes a lot of time. And we are trying to continue with your feedback. With these things, thanking you, each one of you. Also, I thank my colleague Rajini Verma for taking a lot of pain to send the emails and propagate the AFOM webinars and all other things. So thanks to Rajni Verma, thanks to Shivam for preparing this logo of the AFOM school. Each one directly and indirectly who has helped to make this AFOM activities popular. Thanking with this thing. See you soon on 7th, 8th of the July in our AFOM school webinar. Thanks to all of you. Have a nice day. Stay safe. Thank you. Bye-bye.